Good afternoon, everyone, and thank you for joining us for today's workshop and module. Before we get started, I would like to go over a few housekeeping items with those of you that have just come into the room. For those of you that we do have in the room, the first thing I would like to make mention of is our chat pod, which is located on the left-hand side of your screen marked chat. This chat pod is going to be the best way to communicate with us should you have any questions regarding today's material. All questions pertaining to the material will be retained until the Q&A session that will be held at the very end of today's event. So please feel free at any point of today's event to go ahead and type in your questions there in the chat pod, and then we will pull them out and house them in our Q&A cache, and then we will get them answered at the end of today's presentations. This chat pod is also the best way to communicate with us should you experience any technical issues. If you do have any technical issues, please make sure to let us know there in the chat pod, and we will be sure to get you taken care of. This is a brand new platform that we are working with. We launched it last week, so this will be our third event in this new platform. So there are some kinks and some bumps that we are still working through. Your assistance in letting us know if you do have any technical issues is greatly appreciated. We do have a few minutes, so before we do get started, we always like to find out a little bit more about our audience and just to make sure that your chat functions are working properly for you. So if you could take a few moments to type in the chat pod there on the left-hand side of your screen where you are watching today's event, that will give us a great indication about our audience as well as the kind of reach that we are able to obtain with our events with the FTCOE. There was a question about a break. This is a long event. We will be having a break between presenters 2 and 3. It will be around a 5-minute break. So that way everyone can take a break, get up and stretch, and then come back for the rest of the presentations. We've got about 6 minutes before we get started, so I'm going to mute my line back and we'll let the rest of the people come into the room. We have a large crowd today, and then we will get started here right at the top of the hour. Thank you for joining us today.
Recording has started.
Good afternoon, everyone, and thank you for joining us for today's workshop series. This is the second module of the workshop series on probabilistic genotyping. My name is Josh Vickers, and I will be your host for today. Before we do get started, I would like to go over a few housekeeping items with those of you that we do have in the room. For those of you that have joined us, the first thing I would like to make mention of is our chat pod, which is located on the left-hand side of your screen marked chat. This chat pod will be the best way to communicate with us should you have any questions regarding today's material. All questions pertaining to the material will be retained until the Q&A session that will be held at the very end of today's event. So please make sure that if you have any questions throughout the event, please go ahead and type them there in the chat pod. We would hate for you to forget them, and we will pull them out and house them, and then we will have them answered during our Q&A session after everyone's presentations. This chat pod is also the best way to communicate with us should you experience any technical issues. We do see that there are a few that are experiencing some technical issues, and we are working through them. But please make sure that you do type those in there, and either myself or one of our customer service representatives, Tyler or Julian, will be helping you out and getting you set up there if you do have any technical issues. Some things that we have noticed, you do want to make sure that you have hit the play button. It should be in the very middle of the event window and live stream window. If you move your mouse around in it, there should be a play button there. If there is not, sometimes it is also below the live feed window. We have found that Internet Explorer is not compatible with our new system. It does not support HTML5, which is one of the newer streaming services that are out there. So if you are using Internet Explorer, I would suggest that you switch to either Firefox, Chrome, or Safari. Those have been giving us the best experiences for our attendees. So just a few little things there that can hopefully help everyone be able to experience and participate in today's event. All of your audio is going to be streaming through your computer speakers for today's event. So please make sure that you have your speakers turned all the way up, and that or your headphones are turned up as well. That way you can hear today's audio. Before we do get started, we do like to find out where our audience is joining us from. So if you could take a few moments to type in the chat pod there where you're watching today's event from, that'll give us some great feedback and information about our audience, as well as the kind of reach we are able to obtain in the forensic community. We are going to have a large group in today's module, and we do have 4 presenters. So we will be getting started here shortly. I'm going to mute my line back, and then I'll be coming on at the top of the hour to do some introductions, and we will get started. Thank you for joining us today. Good afternoon, everyone, and thank you for joining us for today's module. My name is Josh Vickers, and I'm with RTI International's Forensic Technology Center of Excellence. Today is Module 2 of our Probabilistic Genotyping workshop series. We do have 4 presenters today. We have Dr. David Balding, Dr. Michael Coble, Stephen Myers, and Dr. John Buckleton. Just a quick disclaimer, the opinions, findings, and conclusions or recommendations expressed in this presentation are those of the presenters and do not necessarily reflect those of the Department of Justice. Any products and manufacturers discussed are presented for informational purposes only and do not constitute product approval or endorsement by the U.S. Department of Justice. I would like to hand things over to our moderator for today, Ms. Tamara Moretti with the FBI Laboratory. She's developed this series as a forum for experts in the field of statistical genetics and probabilistic genotyping to share their knowledge and experience as the forensic DNA testing community transitions to ProbGen. She'll be moderating today's module on the elements of DNA profiling, interpretation of probabilistic genotyping. We'll switch to our first presenter, and Tamara, if you'd like to go ahead and introduce our presenters from here.
Sure, Josh. Thanks so much. Welcome, and thank all of you for joining us today for this, which is our second session in the series Probabilistic Genotyping of Evidentiary DNA Typing Results. And today we're going to be talking about statistical genetics as relates to probabilistic genotyping. We are very privileged to be joined today by some of the most distinguished professionals in our field who have graciously offered to share their knowledge and experience with us. Today our speakers, they are the people who have developed theory. They've tested and researched that theory. They've developed SOPs and applied these approaches to casework. They have reported and testified using these statistical concepts, and they have trained members of their own agencies and people worldwide. So I don't know that a speaker series could get any better than this, and I'm very pleased that they're joining us in this same web space. So thank you all to our speakers. I'd like to begin by welcoming them. First, Dr. David Balding is going to be speaking us through a recording. Now, Dr. Balding is 14 hours away from us. I think it's around 2 a.m. his time. So although we have him through a recording, I'd still like you to post questions that you may have for Dr. Balding, and if we can't answer this today, we'll answer them in our final session, which is going to be our panel discussion and Q&A session. Dr. Balding received his bachelor's in math from the University of Newcastle in Australia and a PhD in applied probability from the University of Oxford in the UK. He has held academic posts in London, including the Imperial College of London and University College London. He was a member of the Expert Advisory Group in the UK, Forensic Science Service, and the DNA Specialist Group in the UK, Forensic Regulator. He has given expert evidence in hundreds of court cases, and after 30 years in the UK, he returned to Australia, where he is presently Professor of Statistical Genetics at the University of Melbourne and Director of Melbourne Integrative Genomics. He is lead editor of the Handbook of Statistical Genomics, of which the fourth edition will appear later this year. Our next speaker today is going to be Dr. Michael Coble. And Josh, if you could proceed on the slide for me, please. Thank you. Mike is Associate Professor and the Associate Director of the Center for Human Identification at the University of North Texas Health Science Center in Fort Worth, Texas. He received his bachelor's degree in forensic science and a PhD in genetics from the George Washington University. He is a fellow of the American Academy of Forensic Sciences and a member of the International Society of Forensic Genetics, ISFG. He serves as a member of the OSAC Biological Data Interpretation and Reporting Committee, and I have had the pleasure of working with Dr. Coble for many years as he's an invited guest at the SWGDAM, at SWGDAM. He is a co-editor of Forensic Biology subject area of Wire's Forensic Science Journal and is a member of the editorial board of FSI Genetics. Following his talk, we are joined by Stephen Myers, who has 30 years of experience in the field of forensic serology and DNA analysis. For the last 28 years, he has worked with the California Department of Justice, Jambusinski DNA Laboratory. His primary duties over time have been casework and method development, as well as teaching through CalDOJ's California Criminalistics Institute. He is a member of SWGDAM and OSAC, through which he has helped to create documents relevant to the topics we're speaking about today, as well as likelihood ratios, familial searching recommendations, validation of probabilistic genotyping systems, assigning propositions for likelihood ratios, and reporting genotyping results as likelihood ratios and using verbal scales. Some of those topics and documents that he's contributed, I hope you all are very familiar with those documents. Whether it's kinship analysis or probabilistic genotyping, Mr. Myers believes his belief is the same. If you understand the meaning, formulation, and underpinnings of your likelihood ratio statistic, you will be more likely to word it correctly in your reports and on the witness stand. So you can see why we're lucky to have him joining us today with that philosophy. And our last speaker today, we're privileged to be joined by Dr. John Buckleton. He is a forensic scientist for the government in New Zealand, specializing in DNA interpretation, firearm scenes, and general forensic casework in the laboratory. His caseworking experience covers 35 years in the UK, USA, Australia, Netherlands, and New Zealand, where he has examined over 2,000 cases and testified perhaps over 200 times throughout New Zealand, Australia, England, the Netherlands, and as well as in the UK and the US. I know personally that he has been very instrumental in helping us in the United States as we've transitioned to probabilistic genotyping with a number of the admissibility challenges we've had here in the United States. He has co-authored over 200 significant publications in the forensic field, which includes shoe prints, firearms, DNA, blood grouping, tool marks, fire debris, glass, and paint, a wide variety of experience. He lectures at the University of Auckland, Department of Statistics, and from 1988 to the present, he has presented DNA and glass courses to practicing professional forensic scientists in a number of countries. He has supervised 5 PhD students in the field of forensic interpretation and has been involved in international research and development programs in the area of forensic interpretation of glass and DNA, including expert systems. He is co-developer of the probabilistic genotyping software StarMix. So thank you all for agreeing to help us today with this session. And with that, I would like to turn it over to Josh to start the recording from Dr. Balding. Thank you.
Melbourne, but those of you that have been in contact with me in the past might know that I spent most of my career in London at various universities there. So a little bit about me. My background's originally in mathematics, and you'll see a little bit of it today, but not too much. Most of my career has been in universities in the UK and now in Australia, doing genetics, but mathematical and statistical and computational things in genetics. So that's where I'm coming from. I've done a lot of work on the interpretation of DNA profile evidence. I've helped with a lot of court cases and appeared in court in the UK many times, also a few times in other countries, the US and Australia. So I'm going to be giving you a little bit of my experience and areas that I've worked in on understanding the evaluation of the weight of DNA evidence and conveying it to a court. The particular things I'm going to focus on are co-ancestry, the population genetics effects, and a little bit about sampling. But I'm going to start with just some general issues about evaluating weight of evidence using likelihood ratios. So you'll see that on the first slide here. Other speakers will touch on this as well, but I think everyone has a slightly different perspective, and it's probably useful for me to give you some of my thoughts and a little bit about how I go about these things. So in general, with DNA evidence, we often use likelihood ratios and more for other kinds of evidence as well. And the general idea is expressed on that equation at the top there, that the likelihood ratio is the probability of the evidence given some version of the prosecution case divided by the probability of the evidence given some version of the defense case. So, for example, for a DNA mixture, we might have a known contributor. I'm going to use K for that, but that won't come up much further. But for an unknown contributor, but somebody not of interest, I'm going to use a U for unknown. And in my notation, I'm going to use Q for the alleged contributor, a queried contributor. And then if it's not that person but somebody else, I'm going to use the X for the alternative contributor. So then in this case, our likelihood ratio might look like the formula at the bottom, the probability of the crime scene profile, given that the sources are Q, U, and K. That would be the prosecution scenario here, and then divided by the probability of the crime scene profile, given that the sources are X, U, and K. Now, there's many different possibilities here, and there's many potential complexities I'm going to tell you about. I raised some of these on the next slide. So although we often focus on the likelihood ratio, the world is really more complicated. There's often more than one likelihood ratio, corresponding to the fact that there's more than one possibilities, at least for the defense story. Normally the prosecution makes a specific allegation, but typically the defense doesn't have a specific story that makes up an alternative. So there's multiple likelihood ratios corresponding to things like different numbers of contributors, different levels of relatedness among the contributors. All of the individuals I mentioned previously, the Q, the U, and the K, they can have different levels of relatedness. But the most important thing is the level of relatedness between the Q, the alleged contributor, and what I'm calling X, the other person, if it's not the alleged contributor, the other potential source of the DNA. As well as known relatedness, I'm going to use the term co-ancestry for the kind of unknown level of relatedness, where we're all related, of course, when ultimately we all have common ancestors in many parts of our ancestry. Whether we say that you're related to someone or not is just a question of the known relatedness. If it's a matter of known relatedness, then there are particular match probability formulas that I'm not going to be discussing here today. I'm going to be focusing on this kind of unknown relatedness, and I'll talk more about that later. But for now, I just want to make the point that there can be many possibilities for the defense story and for the likelihood ratio. It is unfortunately complicated. I don't think there's any avoiding that. There's no simple shortcut. That the evaluation of evidence is complicated, just reflecting the fact that reality is complicated, and there's no avoiding it. But in order to convey ideas, we're going to go back to a relatively simple idea from most of the rest of this talk, and just assume there is a simple defense story, and therefore a single likelihood ratio. So let's go on to that and just look at the question of, let's suppose we have a likelihood ratio. It's a meaningful evaluation of the evidence. What are we going to do with it? Well, that's also a complicated question, and once again, there isn't any easy answer to it. Courts have rules and on what is allowed, and of course those rules vary across different jurisdictions, different states, and different countries. So just as there's the complexities around computing the likelihood, there's complexities around how you can present it in court. But what I want to focus on here is the idea that if you want to be an expert in conveying evidence to the court, it's very useful for you to be able to do probability calculations under a range of possible scenarios, and that can be useful to help your understanding and also to help explain to others involved in the case in the pre-trial preparation to lawyers and so on what the likelihood ratio means. So I give one simple hypothetical example here, and we're going to do a few more in the rest of the talk today. So here, let's just imagine that the likelihood ratio is 1 million, and we just accept that for the moment. So one way you can think about that is through this example of, let's suppose there are 1,000 men who could have been the source of the DNA. There's the one who's alleged to be the source, Q, and 999 others. And for the moment, we'll just assume they're all unrelated. Forget about relatedness and Collins is true. So if each of those 1,000 men is initially equally likely to be the source of the DNA, then the DNA profiling results, represented by that likelihood ratio of 1 million, changes the probability that Q is the true source from 1 in 1,000 up to about 999 in 1,000. So that's one way of expressing how strong the evidence is. It's just a hypothetical scenario, but I think it's quite intuitively appealing and giving understanding. And by the time you explain a few little scenarios like that, then I think people are able to get the core idea. It's important to notice, again, I keep emphasizing that reality is complicated and the assumptions that there are 1,000 possible sources of the DNA and they're all equally unlikely, they're never going to be strictly true. But it's still useful to make these illustrative calculations to help you understand and help you to explain to the lawyers before the trial, and ultimately, I think, to help you to explain to the court. So one way to deal with the fact that these assumptions are not exactly right is to try a range of alternate calculations. There's also a simple kind of shorthand way of doing these calculations that helps you think through them quickly, represented here in using the odds language. So odds are closely related to probabilities. It's not quite the same thing, but when the odds are small, they're almost the same as probability. Remember, odds is probability divided by 1 minus probability. So in this example, we would say that we have a prior odds on Q being the true source of 1 in 1,000. So there's 1,000 men, Q is just one of them, and we believe that the DNA came from one of them. Then we multiply by the likelihood ratio of 1 million, and that brings us to a posterior odds of 1,000 to 1 that Q is the true source of the DNA, and that posterior odds is about the same as 999 in 1,000 probability. It's not exactly, but it's close enough. So in order to think through the usefulness of this situation, I want to go back to a common example. Maybe this is the canonical example of evaluating weighted evidence. And I imagine that many of you have already seen this example before, the rare disease testing example. But I wonder how many of you can really get these answers off the top of your head in a straightforward way. And I think that's rarer, and I think it is a useful skill to develop. Often I use these kind of examples in teaching, and sometimes the students say, oh, we've seen this before, but they still tend to get it wrong. So it's worth going over a few times. So here's the scenario. You've got a 1 in 100,000 chance of having the disease. You've got an accurate test. The false positive rate and the false negative rate are both just 1 in 1,000 or 0.1%. The test result comes back positive. What's the probability that you have the disease? So many people make the mistake of overemphasizing the fact that the test is very reliable and think that a positive result from a reliable test means that you must have a high probability of having the disease. But in fact, that's not right. And those of you familiar with this problem will have figured out already that in fact, with these numbers that I just made up here in this example, the probability that you have the disease is only about 1%. So for those who aren't familiar, you might be wondering why is this true? So here's a way of thinking about it. Imagine 1 million people taking the test. Remember, 1 in 100,000 have the disease, so that's 10 in a million will actually have the disease. So the true positive rate is more or less irrelevant, even if the true positive rate is 100%. So there are nobody who truly has the disease is test negative. So in other words, there are no false negatives. Even if that's the case, it will still be true that the 10 who actually have the disease are kind of swamped by the large number of negatives who incorrectly test positive. So in other words, the false positives. So with my numbers of 1 million individuals and a 0.1% false positive rate, that correspond to 1,000 false positives. And as I said, that swamps the 10 true positives by about 100 to 1. And so we end up with about a 1% probability to have the disease. So again, in the odds form, using the likelihood ratio shorthand that I've been mentioned before, we start with prior odds of 1 in 100,000. The likelihood ratio is 1,000, and that leads to posterior odds still of only 1 in 100, or about 1%. So we're still far from certain to have the disease despite this positive result from a reliable test. So that calculation never applies to a particular individual, because there's always factors about you. Your age is different from others. Whatever your medical history is different. So all of those factors would tend to change slightly the true probability view. And of course, there's no such thing as a true probability at all. It's just a measure of how much you know. So although it's never exactly right, just as these hypothetical calculations that I'm recommending for DNA evidence are also not exactly right, it's nevertheless really helpful to think through these examples and to gain understanding of the meaning of the evidence. In the past, this was quite controversial, but it's not anymore. And at least among public health professionals, it's still controversial in the public, because whenever some controversial new disease comes up with swine flu or whatever, there are calls for mass screenings. But the public health professionals now pretty well understand that mass screenings generally are not a good idea for if the condition is rare, because the true positives are swamped by the false positives. And there are similar gains in understanding from the corresponding probability analyses for DNA profile evidence. Again, all of the calculations that I'm proposing are never going to be exactly right and can't be presented in court as the truth or solving the problem, but they do help understanding and do guide you to good ways for presenting the evidence. The first insight from probability analysis of DNA evidence is the one that I've already discussed to some extent, but let's take it a little bit further. In order for the DNA evidence to convincingly identify one of the possible sources of DNA, the likelihood ratio needs to be much larger than the number of possible sources. That's a kind of rough rule of thumb, but it is relevant in particular cases. Of course, we know in many cases DNA evidence is so overwhelming that none of these considerations matters much, but in some cases for complex profiles that's not the case, and so we do have to be able to think these through. So let's now think of a complex profile. The likelihood ratio is just 1,000, relatively small, but let's keep it simple. And in that scenario, whether or not that likelihood ratio is convincing in identifying Q as the source of the DNA depends in large part on how many possible sources there are. So if there are only 10 men who had access to the evidence item, then a likelihood ratio of just 1,000 can still be enough to be convincing that Q is the cause. Of course, we never absolutely prove anything, but the calculation there suggests prior odds of 1 in 10 times a likelihood ratio of 1,000 leads to a posterior odds of 100. So in other words, about a 99% probability that Q was the source of the DNA. This corresponds closely to a case I was involved with in the UK, where there were 10 men who had access to a gun, and that was accepted as part of the evidence. The question was which of those 10 men was the source of the very degraded and partial DNA profile, for which we only had a relatively small likelihood ratio, not 1,000, but not too far off that. The defense lawyer said, in fact, I think the likelihood ratio was 200 in that case. And the defense lawyer said, likelihood ratio of 200, that's nothing, where that corresponds to only weak evidence. But I was able to, I think, persuasively argue that likelihood ratio, when we're only picking among 10 men, can be quite strongly convincing that one particular one of them was the source of the DNA profile. But of course, if we're in another scenario, maybe in a big city where there's 1 million men who could have been the source of the DNA, then that same likelihood ratio of 1,000 isn't convincing in identifying one particular man, because we would have a prior odds of 1 million. The likelihood ratio of 1,000 would just bring that up to posterior odds of 1 in 1,000. So it's still unlikely to be him. It's more likely to be one of the other 999,999 men. So that's another way of getting back to the point I made earlier, that the likelihood ratio is just one ingredient of the calculation, one that the court has to do. It's just one summary of the evidence, but it's not the full story, as this illustration shows. Another controversial issue in the past was, what's the effect of the DNA evidence on a database search? In other words, a DNA profile match arising from a database search. Every now and then this controversy keeps coming back, and although the issue has been settled in the literature many times, it still never kind of fully goes away, because it's very counterintuitive for many scientists. We're used to the idea of hypothesis trawling, fishing for hypotheses as weakening the evidence. And you think if you search 1,000 profiles in a database, that's 1,000 opportunities for a match, and therefore the match is 1,000 times weaker than it would have been given just a single suspect. But doing the probability analysis correctly shows that that's not right, that in fact the overall case is slightly strengthened because of the 999 or whatever non-matches in the database. So, as I said, that's counterintuitive. Perhaps one reason to think about that is that when in science generally we're thinking about multiple hypothesis testing, it's usually not the case that we know in advance that one of the hypotheses is true. But in a forensic DNA situation, we know that somebody left the DNA in that evidence sample. That's pretty much certain. So there is somebody out there who matches and who is the true source of the DNA. The more you search and exclude people who don't match, you're limiting the pool of possible suspects, and so increasing the strength of the evidence. Typically, the increasing effect will be quite weak, so to roughly speaking, the evidence stays equally strong. But it's important to know that the searching in the database, it does not weaken the evidence. If you thought it weakened the evidence, then you weren't setting a high enough threshold in the first place about how convincing the evidence need to be. Another way to think about it is that if your database gets increasingly large to include the whole population, then a single match in the database must be completely convincing that we've got the right guy, because then if the database was the whole population, then we would have excluded everyone else. And so the one match must be the right guy, as long as there hasn't been any kind of error. So I've got a reference here for further on that topic. Again, this issue does come up from time to time, but I think this the point of view that I'm expressing here does follow from the probability analysis and is now pretty widely accepted. But one other complexity that can be resolved by doing some illustrative calculations involves the situation I raised earlier, that there can be multiple defense possibilities, multiple defense stories, and they can have different likelihood ratios, and how do we combine them? And again, at the risk of repeating myself too many times, there's no complete answer to this challenge, but by doing some illustrative probability calculations, you can get guidance and understanding. So in this particular case, which was a very well-known case in the UK because the victim's boyfriend was originally convicted, and this became a very high-profile miscarriage of justice. He was eventually released, and another man was accused of the crime, and there was some DNA evidence supporting the identification of this other man, and associated that with a likelihood ratio of 200 million. So normally we'd say that was extremely strong evidence, and that might, with very little supporting evidence, be sufficient for a prosecution. However, in this case, the suspected contributor Q had 3 brothers, and two So the reference profiles for those brothers were available to the investigation. 2 of the brothers were quickly excluded, but one of the brothers, let's just call him B1, came up with his reference profile, produced a likelihood ratio of 150,000 in favor of him being the source of the DNA. So this had the lawyers and everyone involved in the case quite perplexed, because how can there be very strong evidence against the brother B1 when, if we believe the prosecution case, we know that he wasn't the source of the DNA, it was his brother. And again, there's no complete resolution to this problem, and it's true that had we only observed B1 and we never observed Q, we might have convicted the wrong man. There is always some chance of a mistake, even with the best and most rigorous presentation of the evidence. But in this case, I was involved in assisting the prosecution, and I gave evidence in court, and I was able to use an illustrative probability calculation such as the one presented in this table here. So I suggested, well, let's just suppose there's 1 million men who could be the source of the DNA. There's our alleged contributor Q, there's his 3 brothers, and then there's 999,996 other men. So if initially we assumed they were all likely to be contributors, then the posterior probabilities are as illustrated here. 994 in 1,000 probability that Q was the source of the DNA, somewhat less than 1 in 1,000 for B1 to be the source. B2 and B3 were pretty much excluded, as I said, and then all the other unknown possible contributors. In total, there's a probability of 5 in 1,000 that the DNA came from men. So if you just accept this calculation for the moment, the 1 million unrelated men, approximately 1 million, are collectively more likely than B1. So there's nothing, in that sense, there's nothing very special about the case that there was this alternative possibility B1. Although 150,000 likelihood ratio would normally be regarded as very strong, it's very hard just sort of automatically, mentally, to appreciate the fact that 200 million is so much bigger that the 150,000 is not very important when compared with 200 million. This calculation, I think, illustrates that effectively, and of course it relies on assumptions that aren't true exactly, but it really, I think, helps guide intuition. I think the court was really helpful in that case in allowing me to present this illustrative calculation to the jury. I understand that that wouldn't be possible in some other jurisdictions. It's always difficult to say, but I think it was helpful to the court, and Q was, in this case, convicted for this crime. So let me now get on to the sort of headline topic for my talk, which has got to do with population genetic factors and co-ancestry, and the parameter FST, which is also often called theta. I'm going to call it, refer to it as FST. So as I mentioned, there's known relatedness, and there are match probability formulas given known levels of relatedness, but we're all related, and this FST parameter and the concept of co-ancestry is a way of measuring the unknown shared ancestry of 2 individuals given remote common ancestors that they don't explicitly know. The value of FST has several different definitions, several different ways of estimating it, and it can be explained in different ways. There's always, as usual for complex topics, there's been some controversy, some misunderstanding about FST, so I'm giving you my interpretation, which I think is the most useful way of thinking about it for the forensic context, but that other people might present it in a different way. But one thing that's important here is that the FST is computed for forensic purposes relative to a reference population. For all purposes, it's relative to a reference population, but what's different is that for many population genetic applications, the reference population isn't observed, but is just inferred in a statistical calculation. But in our case, in the forensic situation, the reference population is the population from which the available allele frequency database is observed. In any case, I'll come to that in a moment, but in general, the idea is that two individuals that come from an isolated population, they might be have relatively low co-ancestry for that population, for that community, but nevertheless high co-ancestry relative to the broader population. So co-ancestry is a kind of a relative topic. If we're given two individuals, we can't just say what is their co-ancestry. It's a kind of meaningless thing in general. We have to say what is their co-ancestry relative to this reference population. So that's a key point that I want to emphasize. And in the forensic situation, we've generally got allele frequency databases from fairly broadly defined populations. In the UK, we've used databases with titles like Caucasian or South Asian or East Asian. They're broadly defined populations. So it can be quite often the case that the alleged contributor Q and the alternative contributor X have relatively high co-ancestry for that database population. So one way to have high co-ancestry, or one way to think about it, is that they come from the same subpopulation, so that if the total population where the reference population is, for example, South Asians, then maybe the relevant subpopulation is from a particular region in India or Pakistan or something like that. So that's one way of thinking about it, but we don't really have to have the concept of subpopulation. It's really just talking about how much shared ancestry is between these two individuals. So given that little preamble, if we just believe that we have a value of FST, there's a very handy sampling formula, I call it, for the probability of a sample of alleles drawn from a subpopulation, say, or from a group of individuals with the same level of co-ancestry. And that is represented by the formula given here. That's a kind of sequential sampling formula. So given that you've sampled so many alleles, and this many of them are of the allelic type you're interested in, let's say allele 9, and the rest of them are of other allelic types, then the probability that the next allele is also of type 9 is given by this formula here. So when FST is 0, that just simplifies to P, which is the frequency in the reference population of the allele. So that would be the scenario that people would be familiar with in sampling the individuals from a population with known allele frequencies. So the answer would be just that every allele drawn has probability P to be the allelic type we're interested in. The complication that we're modeling with this sampling formula is that we don't know the allele frequencies because we're sampling in a subpopulation which has different allele frequencies from the total population, and we don't know the allele frequencies in the subpopulation, but we do know the FST, which measures the co-ancestry of individuals in that subpopulation, and we do know the allele frequencies in the reference population, or at least we've got good estimates of them, and then you can use this sampling formula. So in general, for situations where we're interested in FST is bigger than 0, and so the probabilities change. It's not just fixed at probability P for every drawing of an allele. Because we don't know the allele frequencies in the subpopulation, every time we see an allele 9, that increases the probability that the next allele will be a 9. And it increases it exactly according to this formula under some simplifying assumptions. Like everything, the formula is not exact, but it works pretty well. So, for example, although the probability that the first allele drawn is a 9 is just P, the probability that two alleles drawn are both 9 is not just P squared, which would be the case in the independent sampling case. It's P squared plus an extra term depending on FST. So the bigger FST, the bigger the learning effect that the first allele drawn being type 9 gives you more information about the second one being type 9, again, according to this formula. So you probably never need to use this formula because it's built into software, but I think it's just useful to make the point here. So there's no need to kind of know it exactly, but I just want to make the point that it's a relatively simple formula, and with a bit of practice, it's not that hard to use. And continuing in this way, you can build up probabilities for any observed sample of alleles. Now, for single locus match probabilities, typically in the simplest scenarios, under the defense story that the alleged contributor is not the true source of the DNA, then we've observed DNA from two individuals, one in the crime scene profile, and we've also seen the reference profile of Q. So under the defense story, they're two different people. So we've seen 4 alleles from those 2 people at any one locus. But of course, under the prosecution story, that Q is the source of the DNA, we've only seen one individual. We've seen Q's reference profile, and we've seen the crime scene profile, which under the prosecution case has come from Q. So in that case, we've only seen the 2 alleles from Q. So we just need to use that sampling formula under the defense case 4 times for the 4 alleles, and under the prosecution case 2 times, and the match probability is the ratio of those 2 numbers. The calculation is not too hard to do, and I've given the answer here, which is possibly familiar already to many of you, that under certain simplifying assumptions, we obtain these match probabilities. They have the probability that the homozygous, so that observing one allele of a certain type makes it more likely to see more alleles of that type and less likely to see other alleles. That's the sort of intuition that's built into these formulas. The higher FST is, broadly speaking, the higher the probability of a match, but not always the case in the heterozygous case. There are some counterexamples. Now, having got single locus match probabilities for the alleged contributor and the alternative true source of the DNA having a co-ancestry represented by FST, having got that for one locus, we then want to combine the loci. And the natural thing to do is to multiply them, but if you've studied some probability, you'll know that you can only multiply things together you can only multiply probabilities together if the events are independent. So we have to ask the question, are matches at different loci, genetic loci, independent? And just as I said, it's a bit meaningless to talk about the co-ancestry of 2 individuals on its own because it's always co-ancestry relative to a reference population. It's also true that independence is a bit meaningless on its own. Although we might often talk about 2 things being independent, broadly speaking, independence is a matter of what you know, and you have to be explicit about the reference information in order to answer the question of whether or not 2 events are independent. And one example I like to use is that shoe size and reading ability in children are correlated. They're not independent. And it's pretty clear that the kids with bigger shoe sizes read better. From a data set, you'll back that up pretty convincingly, I'm sure. Now, that seems a bit surprising because we know that shoe size doesn't have, or we would think that shoe size doesn't have any causal relationship to reading ability. And in this case, there's a simple explanation that age is the underlying relevant factor because older kids have bigger shoes and better reading ability. So although it's true that shoe size and reading ability are, broadly speaking, not independent, they're correlated, but if you condition on the relevant information of their ages, the 2 are approximately uncorrelated and approximately independent, and correlated and independent mean roughly the same thing for our purposes here. There's a technical difference. So there's a similar idea with whether or not matches are independent across loci. So broadly speaking, they're not because of the unknown relatedness between the two individuals. But if you condition on the relatedness, and here in this sense relatedness to include the remote unknown relatedness, that is the co-ancestry, then matches are approximately independent. There are, some possible reasons for not independence related to things like selection and so on. But broadly speaking, it's relatedness, which is the big relatedness and co-ancestry, which is the big important factor. So that in general, asking is the product rule true for multi-locus profiles? There isn't a simple answer to that. You have to say, well, it depends on what we know, and if we have got the relatedness and the co-ancestry right, then the matches at different loci are approximately independent, and it's okay to multiply probabilities together. This is a convenient point just to point out the note at the bottom of the slide here that I started off talking about likelihood ratios and then switched to match probabilities. So here's the point to explain the connection. For the purposes of working with co-ancestry, it's much more straightforward to talk about match probabilities. Match probabilities is a more intuitive concept. They're related. Likelihood ratio could actually be defined either way, but conventionally we define the likelihood ratio to be such that big values correspond to strong evidence, whereas for matches, small values corresponding to strong evidence, and they're related just as inverse as indicated here. However, although this relationship holds in the simple setting of a single contributor profile where a match is a well-defined thing, but for complex profiles, there is no such thing as a match, generally speaking, so the match probability doesn't exist. So the likelihood ratio is a more general concept and makes sense for complex evidence profiles as well as in the simplest case. So I would suggest that when matches make sense, which is typically only for single contributor profiles, some simple mixtures, then let's talk about match probabilities because that's easier to understand. But for complex profiles, we need to use the language of likelihood ratios. As we've discussed before, people don't like it because it's a bit complicated and unfamiliar, and that's unfortunate, but we've got to try and work with that because there's no alternative good way of evaluating evidence and presenting evidential strength. Now, I've said that if you've got the correct value of FST, then it's okay to multiply across loci. Of course, we don't know the correct value for FST, and we never will know the correct value in a particular case. There's lots of reasons to argue for using a relatively high value compared to the reasonable estimates. But what we need to know is the level of shared relatedness between our alleged contributor Q and the alternative contributor X. And of course, there are many possible X in general, and they'll have in general different co-ancestries relative to the available forensic database. We're never going to know the right answer to that. But what we can do is compute FST for a lot of scenarios and then use a relatively high value. As I said, as well as we should use a high value just because of the fact that we don't know, and the higher the value tends to weaken the evidential strength, and so we're being conservative in a sense. But also, once we multiply across loci, we've got a product that involves many FST terms. We don't know FST, so we should have a probability distribution on it. That gets a bit complicated, so in practice we don't do that. But the average over products of an uncertain value is dominated by the high end of the distribution. So there is a bit of a technical reason here that I just hinted at for using high values of the reasonable distribution of FST estimates. Now, there are a lot of estimates of FST in the population genetics literature. Typically, as I mentioned earlier, the reference population is regarded as unknown in the population genetics literature. And so those estimates are generally not directly appropriate for forensic applications, and they're often too small because the inferred unknown reference population is inferred to be similar to the individuals in the study. Whereas for a forensic database, there can be quite a difference between the individuals of interest in a particular case and the individuals in the database. And therefore, the nature of the reference population is important. So although there are many estimates of FST, and there are some limitations to the study that I'm going to tell you about here, this is the one study that I'm aware of that at least uses the forensic context of a reference database taken exactly from the forensic databases used in the UK. And the reference populations used are indicated by the colors in the map here. So there's sub-Saharan Africa, which also includes some islands of the Caribbean. There's North Africa and West Asia covered in green here. There's South Asia, India, Pakistan, Bangladesh, and neighboring countries. Also Afghanistan is included there. There's East Asia, and then there's the Caucasian database, which includes Europe and European origin populations in the Americas and Australia. In this study, we looked at samples from national populations and compared them to these reference forensic database populations that are sort of really continental in scale. Now, again, that's not the right scale because a national population will typically include quite a bit of genetic diversity. And so, if we're really talking about isolated subpopulations in one particular region of a country maybe in a mountain valley or something like that, then typically a larger value will be appropriate. But by looking at many national populations and comparing them with the reference populations, we're able to get some idea of relative numbers. So here's just a snapshot of some of the results in that paper. And these are comparing some African national populations with a general Afro-Caribbean database population. So the numbers here are for different percentiles of the F distribution, 2.5 percent point, the 50 percentile, which is also the median of the distribution of FST, and the 97.5% point. And because of the arguments I made for using a high value, I've recommended to look at the 97.5% point as being in the upper tail of the distribution. I put those values in a red box here, and you can see they're typically between about 1 and 2%. It's actually surprisingly low in a way. Even Jamaica, with its distinct history being in the Caribbean, has a relatively low FST estimate compared to this database. So we did similar calculations for the other populations, South Asians and East Asians and so forth, and we generally reported that the 97.5 percentile was almost always under 3%. However, that deals with the situation that Q and X are coming from the same national population and looked at the FST value relative to a continental scale database. But what if Q and X are actually from different populations? So I've got a reference here to another paper. You notice I'm citing my own papers, not to say that others haven't done good work, but I'm best able to explain to you my own work. So I'm referencing a paper that I've done also in 2014, and I'll give the full reference to these papers in a few slides, where we looked at the situation that, in fact, the alternative contributor might come from a completely different part of the world from the alleged contributor. Now, I don't have time really to explain these diagrams here. They're just briefly to whet your appetite. But basically, we're looking at the strength of the evidence given that the likelihood ratio is computed over all possible values of the reference population for Q and for X. And comparing that with a kind of heuristic that no matter what the ancestry of X, we're just going to use the database relevant for Q and a relatively large value of FST, which, as I already said, 3% we found to be a satisfactory large value. And if you use the database of Q and an FST of 3%, then your likelihood ratio, these diagrams show the difference between the likelihood ratio computed using that heuristic and then using the correct reference population is always negative in these diagrams. In other words, that corresponds to it always being conservative, better for the defendant to use the database relevant to Q and an FST of 3%. So that's kind of helpful to prosecutions because it says we don't have to worry about the fact that the ancestry of X might be quite different from Q. As long as we've used a satisfactory value of FST, that will be good enough. And again, I haven't proven that 3% is good enough. There's never a perfect answer to these questions, but we've given over our various papers quite a bit of evidence that 3% is pretty conservative under many scenarios. Now, so that's dealing with the fact that we don't know FST and coming up with a general argument that 3% is often good enough, but not always. There's also the issue of sampling error in the database frequencies. Of course, we don't know the database frequencies. I said earlier we know the P, but of course we don't. We've just got estimates from a database. But because of the importance of the effect of FST, I think the effect of any uncertainty about the P is relatively unimportant, as I argue in this slide. I've proposed in the past some little adjustment represented by this formula in the middle of the slide here, where you just add 1 to the heterozygous allele count and add 2 to the database allele count in order to get an estimate which is biased slightly upwards, so that the estimate is never 0, even if the allele has not previously been observed in the database. I think it's useful to make this simple adjustment. There are other alternatives that you can argue for, but my overall argument is that FST is the leading story, and once you've dealt with that, sampling error in the P is not terribly important. Now, as I've argued many times, there's no correct answer to for the likelihood ratio. I want to just emphasize that point again here. There's no true probability of rain tomorrow, and there's no true weight of evidence against a defendant. There are values that summarize our information. They vary with the information available to us. The probability of rain tomorrow varies with what information we've got. The likelihood ratio for somebody to be a contributor of DNA varies with what information we've got, and that information, broadly speaking, about all the factors that are involved in a DNA profile, about artifacts like stutter and all of those other things. So there's never going to be a correct answer to that. All we can do is to verify that the likelihood ratio has been computed using an algorithm that's performed well over many tests, and I list here some of the performance tests that are available. There's quite a few other ones. These are just some that I thought up and have used in the past, but there's quite a few others. So we compute the LR using the best available database, using a conservative value of FST, and using an algorithm that performs well under tests such as the ones that I've given here. But still, we're in the situation that we cannot say with certainty to a court that this is the correct assessment of the value of the evidence. And because of that, there's often calls for some measure of uncertainty in the likelihood ratio, like a confidence interval that scientists will be familiar with. When you report an estimate, you generally are expected to report the confidence interval as well. That's not appropriate here. There's a number of reasons that I can't go into in the time available. I think the most useful thing is to do a sensitivity analysis, but again, the most important thing is to have a relatively large value of FST, once that is dealt with, all other sources of uncertainty become relatively unimportant. So FST becomes a sort of general fudge factor for ensuring that our likelihood ratio doesn't overstate the strength of the evidence. It might be a bit too low, but generally speaking, we're prepared to do that to ensure that we're not being unfair to defendants. So here's a summary of the key points that I've made so far. And one of the big overall points is that evaluating evidential weight for DNA profiles or any other kind of evidence, presenting it to a court fairly and comprehensible, are both really difficult challenges, and we don't have complete solutions. There's no mathematical formula or probability calculation that's just going to be a recipe for answering this problem. The probability analyses that I presented using hypothetical scenarios, I think, are really helpful in understanding, but again, they always rely on assumptions that can be challenged and therefore never give a complete and perfect answer to the problem. I've also made the point that likelihood ratio is a key ingredient of the probability analysis. It can be a useful summary, but it isn't the final answer. There, we can often think about multiple defense stories and multiple likelihood ratios. And in fact, we don't even need a likelihood ratio. The reason for using it is that likelihoods are a bit meaningless. And so to present a ratio kind of cancels out some unnecessary factors and gives you something that's a little bit more interpretable. But it's actually not essential, although it is, I assert, very useful. So I've emphasized that one of the most important unknowns, and really I might argue the most important unknown in computing a likelihood ratio, is the relatedness, known direct relatedness, or coancestry, remote unknown relatedness between the alleged contributor Q and alternative contributor X. I've just put it in the singular there, but of course there can be many different X, and there can be different FSTs for them. However, under a range of scenarios, we've found a lot of evidence for the claim that given a database best fitting the alleged contributor Q, an FST value of 3% is typically adequate to ensure that we're not overstating the evidence. There might be some exceptions with small isolated populations or some unusual circumstances, but broadly speaking, I think this is going to be safe presentation of the evidence, provided you've used a reputable algorithm software that's been thoroughly tested and is reliable for computing the likelihood ratio. So I hope you found those thoughts helpful. I've got some further references, and of course I can't resist telling you about my book, which includes many of the topics that I've been discussing here and many other related topics. There was a first edition in 2005, a second edition with my then PhD student, Chris Steele, came out in 2015. The papers I've referred to in the last few slides also were published in 2014, and Chris Steele and I also wrote a review in the Annual Review of Statistics and Applications, again in 2014. That was a busy year for me. So that's the end of the main topic I wanted to talk about. I just want to go on, just before you switch off, I just want to say a little bit more in the remaining minutes about some other work that I've been doing recently that I think is really interesting, and I'd like to just give you a little advertisement for that and some references that I hope might be helpful. And we've been looking at the unilineal markers, Y chromosome and mtDNA, and these have presented a problem in how to present the evidence fairly, really, that's been discussed for decades, and I don't think there's been a really good solution so far. The kind of match probabilities and likelihood ratios that I've been talking about for the autosomal DNA profiles don't work well here because of the unilineal inheritance pattern, that's one parent only, means that in practice matching individuals are always related with a relatively recent common ancestor. So because the space of all possible Y profiles and the space of all mtDNA sequences is so enormous, a chance match between completely unrelated people is negligible. It's just about impossible. But we all have maternal line relatives and paternal line relatives going out over many generations who might have the same Y profile or mtDNA as us. And so it's quite a different scenario. And together with my Danish colleague, Mikkel Andersen, we've proposed a different approach, again, motivated by the probability calculation, but by just reporting an estimate of the number of males with Y profile matching that of Q. We've also proposed a way of adjusting for an observed database count if available. So let me press on to the next slide, which shows some, what I hope are helpful examples. So for certain assumptions about the population size and growth rate that are explained in more detail in our paper in PLOS Genetics here, unconditional refers to the situation where there is no database information about the frequency of this particular Y filer plus profile. Then the median number of men with matching profile is 8 under these particular population assumptions. The upper 95% quantile is 32. The upper 99% quantile is 48. So in other words, there's up to a few tens of individuals matching profile. Now, if we observe a count in a database, so the next 3 rows give observed count of 0 in different database sizes, then an observed count of 1, and then observed count of 2, then that has the corresponding effect on those distributions, but still not a very huge effect. And this comes a little bit counterintuitive for many people, because any particular Y profile is so rare, the database information is very noisy and not very informative unless the database were really huge, which they're not in practice. So really the database information is not that helpful, although it does change the probabilities a bit. But we suggest combining the probability information with our simulation-based estimates of the distribution of the number of individuals with matching DNA profile, Y profile. So there's another result for mixtures, which I think was a little bit surprising. If you've got Y profile evidence from a single contributor and it matches, so let's suppose you've got an idea of the evidential weight there. Now suppose it's a mixture of 2 Y profiles from 2 males, and you've got one alleged contributor who's included in that mixture and therefore could be a contributor. How much weaker is the Y profile evidence when it's a mixture rather than a single contributor? And I think most of us in all the literature so far would suggest that it's quite a bit weaker because there's 2 to the number of loci possible alleles and therefore 2 to the number of loci possible pairs of profiles that could have created this mixture. But in fact, we've shown that the 2 contributor mixture is almost as strong as a single contributor evidence profile. That seems really surprising and counterintuitive. And the reason why is this point that I made earlier, that every possible Y profile is so unlikely that unless you've already seen it, it's pretty much certain not to exist. And so once you've seen a copy of Q's profile, then the best way to explain the mixture is that it either came from Q or one of his relatives with the same profile, and then some other known contributor. That's much more likely than 2 other profiles that happen to make that mixture. So there's the reference for more information on that. We have got, similarly, we've done a more recent paper with doing a similar kind of arguments for mitochondrial DNA, because the mutation rate is smaller for mitochondrial than for Y profiles. The issues are a little bit different. Broadly, it's the same thing, but there is a larger number of matching individuals and so the population demography becomes more important. Again, I give the reference paper for more information, and that's all I've got for you today. I hope you've benefited somewhat from this, and I hope I can deal with any questions later. Thank you for your attention.
Dr. Balding for sharing. We appreciate Dr. Balding for sharing this very informative and helpful information, and also reminding us of his writings, some of which we've included on the announcement for today's session. So hopefully you all can follow up with some of those readings. Now I would like to transition over to Dr. Mike Copel to continue on our session.
Thank you so much, Tamara, and hello and welcome to everyone watching in on the webcast. I would like to, for today, my lecture, to talk about the likelihood ratio and do some sort of hands-on work calculations for related and unrelated individuals. So we'll have some practical exercises. As you recall, next week we will not be meeting. Will be a break, so I'm going to give you some homework to do, and so you can do that next week, and then the following week we will reconvene and go through the answers. Josh has kindly put the link to some worksheets that you can download to use in doing these kinds of calculations, so we'll talk about that in just a few moments. But I'd like to first give my last slide, and I'd like to thank many people who've helped put these presentations about likelihood ratios together. And interestingly, 2 of the 4 will be following, so it's not too intimidating to have 2 of the following speakers to go after me. But Brian Harmon and Stephen Myers from Cal DOJ, Simone Gittleson at the University of Technology in Sydney, and also Dr. John Buckleton from ESR. So our present sort of methods for interpreting DNA, especially when it comes time to provide the strength of the evidence, we've been traditionally in the U.S. we've used the CPI approach, random match probabilities, and also the likelihood ratio. These are all sort of binary methods of interpretation. That is, we require a threshold, not only an analytical but also a stochastic threshold. And that stochastic will help us in determining whether the presence of a single allele, if above stochastic, we can have some confidence that this is a homozygous profile. If it's below the stochastic, then we have to be careful that perhaps we're missing data. So for CPI, there is a restriction on using data where dropout is evident. But with the random match probability and the likelihood ratio, we can use peak height ratios and mixture ratios and so forth to try to limit the number of potential combinations to then provide the weight of the evidence. What we're moving into, and what many labs in the U.S. have already moved into, are probabilistic methods of interpretation. And these methods of interpretation no longer require a stochastic threshold. And so we will either implicitly include a probability of alleles dropping out or dropping in this sort of semi-continuous approach in which we're not using peak heights, or in the continuous approaches, the continuous models, then that type of dropout would be modeled. And we do use the peak heights, and we can also model other things potentially like stutter and variation in peak heights and things like that. So the first step to moving toward a probabilistic approach, of course, is the likelihood ratio. And one reason why, at least in the U.S. and other labs around the world, are sort of motivated for making this change, why should we move to a new method of interpretation, is mainly, I think, because a lot of our kits, we have the new Megaplex kits and the C instruments, sort of the 3500 series and other instruments that are out there, are much more sensitive than in the past. And so we're seeing now potential low-level contributors that may be in a mixture that we may not have observed in using multiplexes in the past, or CE instruments like the 310. And also, in conjunction, the type of evidence that's been submitted to the lab has moved away from mostly high quality, high quantity sort of blood and semen from, say, for example, a mixture of two individuals in a sexual assault, to more and more trace profiles, so swabbings of steering wheels and guns and cell phones and things like that that are generating more sort of higher order complex mixtures, and these mixtures where we have increased stochastic effects. So probabilistic genotyping, and this is just a definition from the SWGDAM guidelines for validating probabilistic genotyping system, is the use of biological modeling, statistical theory, computer algorithms, and probability distributions to calculate, and I highlight here, likelihood ratios. So all probabilistic genotyping software will use likelihood ratios. So this is something that, as a community, we need to move to first and understand before we really, I think, start using the ProbGen systems. It's better if you can do that. This probabilistic genotyping is a tool. It helps to provide statistical weighting. Again, it doesn't use the stochastic threshold, and will either incorporate a probability of dropping in or dropping out, or it will model that. Now, I'm not going to spend a lot of time talking about probabilistic genotyping. There'll be more lectures coming up in this series about that. So the focus today is going to be on the likelihood ratio. And I think traditionally, at least in the U.S., when you mention likelihood ratios, it invokes a little bit of fear into people because it's something that we're just perhaps not really used to. Now, unless you do a lot of kinship cases, you're quite familiar with the likelihood ratio. So I just want to assure everyone, the likelihood ratio does not stand for, the LR does not stand for a lifeless reaper. So you may envision this as facing you when you start doing the LRs, but it's really not that bad. And I also want to point out, since I mentioned reaper, the MCMC, the Markov chain Monte Carlo, which is used in some of these software programs, MCMC does not stand for more cowbell, more cowbell. Now, that's kind of a joke if you know I think one of the best Saturday Night Live skits where they're doing the Don't Fear the Reaper, the song from Blue Oyster Cult. Anyway, if you find that on YouTube, I think it's worth your time to watch. So as Dr. Balding mentioned, he sort of outlined this Bayes theorem. He talked about the odds form, and he mentioned that there were different components, and we'll sort of start in the middle where we have the probability of a hypothesis in the numerator, and we have the probability of a null hypothesis, that is the complement of that hypothesis, in the denominator. And he mentioned that this was sort of your prior odds. And he mentioned the case if maybe there were 10 men involved, and the prior odds may be 1 in 10. And then you multiply that in this sort of Bayesian framework times your likelihood ratio. So the likelihood ratio is a component of Bayes' theorem. In fact, sometimes this likelihood ratio is called the Bayes factor. And what we're looking at is the probability of the evidence given a hypothesis divided by the probability of that same evidence given the alternative hypothesis. And when you multiply your prior times your likelihood ratio, as Dr. Balding mentioned, you get a posterior odds, or in some cases you may hear it called a posterior probability. Now, we are only going to focus on this last component over here, the likelihood ratio. So let's talk for just a moment. If we first look at the likelihood ratio, and again, I think this is where maybe some people get their fear about the LR, is that there's some parts here that maybe look a little unfamiliar. And it's mainly this bar here, which is to denote that this is a conditional probability. And so let's take just one moment and explain what that means. We're looking at the probability of the evidence given a hypothesis. So let's say, for example, and again, this is a slide that I like to acknowledge from Brian and Stephen, we have the probability of an event B given, or if, A has already occurred. So this is what a conditional probability means. Probability of observing an event B given, or if, event A has already occurred. And what this is basically saying is that there's a little bit of information in A event A, that's going to affect the probability of event B. So here's an example. If I were to ask you, what is the probability of rolling a 5 if you have a 6-sided die, what would you say the answer would be? Now I know you can't join the conversation of over the computer, but maybe you're answering in the chat. But I think we could all agree that if I were to ask you what's the probability of rolling a 5, well, that probability is 1 out of 6. There's one chance to roll a 5 out of the 6 possibilities. But now, if I ask you this question, what's the probability of rolling a 5 given, or if, that roll is odd? Well, now this changes my probability, because when I give you some information, for example, that roll is odd, well, now I don't have 6 possible answers. I only have 3. It could be a 1, a 3, or a 5. So the probability of rolling a 5 is no longer 1 in 6, but it's 1 in 3. So this is what a conditional probability does, is it will allow you to calculate the probability of some event given information that is provided to you. So if we look at our likelihood ratio here, we've talked about the conditional probability. The other thing that we're going to talk about here is this part, the E, which stands for evidence, which comes from your electropharogram. So this is the data that you've generated from the evidence in your laboratory with your kit on your instrument. So you have the evidence there. And then the last part of our likelihood ratio is the probability of this evidence given hypotheses, or these may also often be called propositions. And so we may have at least 2, as Dr. Balding said. There's no necessity that you only have one likelihood ratio calculation. In fact, you may have several. In fact, as he mentioned, usually those multiple likelihood ratios come from changes or differences in the denominator down here, the alternative explanation. So we may have an explanation like, for example, in the numerator that the person of interest is a contributor versus the alternative is that the person of interest is not a contributor. I mentioned this paper. It's a classic paper by Dr. Buckleton and Dr. James Curran from the University of Auckland. And they, in this classic paper back in 2008, discussion about the merits of random man not excluded, or basically CPI, CPE, likelihood ratios. And 2 things that they concluded is that A, likelihood ratios tend to be or can be more difficult to present in court. Now, I agree that it can be more difficult to present, but I think once the scientist gets comfortable and familiar with likelihood ratios, it becomes easier. And I would harken back to what Stephen said in his profile, is that the more you sort of understand and are comfortable with likelihood ratios, I think the easier it becomes. And the second real force was that the random man not excluded tends to waste a lot of information, again, with that sort of stochastic threshold, data below the stochastic threshold, often we need to throw those loci away. The ISFG back in 2006 gave recommendations for how to interpret DNA mixtures. And the first 2 recommendations I'll point out, number 1 is that the likelihood ratio is the preferred approach for mixtures. And that, of course, as mentioned by Dr. Buckleton and Dr. Curran, the random man not excluded may waste information and often or sometimes may not be conservative. And the second recommendation is that even if you don't use likelihood ratios, it's recommended that you should be trained and understand and potentially, hopefully one day, use likelihood ratios in your reporting and in the courtroom. Now, as Dr. Balding mentioned, typically in the full Bayesian framework, you would have a prior probability, and then you would use your likelihood ratio to calculate your posterior probability. But since, as a scientist, we're only focused on the evidence, we are just going to talk about the likelihood ratio. in both the numerator and the denominator, we're evaluating the probability of observing this evidence. Again, it has nothing to do with the probability of guilt. It has nothing to do about the probability of innocence. It's simply an evaluation of the evidence. So prior probabilities and posterior probabilities are typically left to the trier of fact, the judge, the jury, and there may be certain cases, like, for example, in Dr. Balding's example, where he was able to present this in this particular court case. But typically, those prior probabilities and posterior probabilities are more or less left up to the jury or judge, whether they know it or not. They're basically synthesizing everything they're hearing in court to make their decision. So typically in the forensic DNA world, we're looking at or evaluating evidence based upon alternative pairs of hypotheses or propositions. Usually these hypotheses are formed as follows. We look at the probability of the evidence given if the person of interest is the contributor to that evidence, or is the stain originated from this one person of interest, versus in the denominator, the probability of the evidence given that this evidence came from some unknown, unrelated individual to our person of interest. So this is typically what we're looking at. And usually in a courtroom setting, there are two sides to the story. You typically have the prosecution's proposition, in which the prosecution may argue that the DNA is from this person of interest, and from the defense side may be arguing that the DNA did not come from the person of interest, it may come from some other person. Again, this doesn't have to be a single proposition. The defense could offer multiple propositions, and there may be complex cases where you have to think about the multiple ways to explain the proposition. And typically, historically, we call this first proposition from the prosecution HP, and the second proposition we typically call HD. Again, it's a sensible explanation of the evidence. It's not meant to be the only defense proposition that could be made. Now, there is, of course, some have argued that maybe we should move away from using this sort of historical HP and HD for prosecution and defense, and that has led to what may appear to be the many faces of the likelihood ratio. So if you're a Game of Thrones fan, the faceless men who can change their appearance. So you may have something like this, where you see either in articles, in publications, where we're talking about the prosecution's hypothesis versus the defense hypothesis. You may also see it as H1 and H2, hypothesis 1 and hypothesis 2, and Dr. Gill used this terminology in last week's webcast. He also used the HP and HD. And there also could be recently a paper from Dr. Buckleton and colleagues mentioned, usually it's not controversial to have the prosecution's hypothesis, but maybe for the alternative hypothesis to say it's an alternative, so have A instead of D for alternative hypothesis to the prosecution. And finally, there could also be this kind of nomenclature where you have the hypothesis of the individual being a contributor to the mixture versus the hypothesis that he's not a contributor. So there are many different ways that you can express this, but they're all saying the same thing. We have a proposition, we have a hypothesis that tries to explain the evidence that is observed versus an alternative hypothesis, or again, historically, the defense hypothesis. We're looking at the probability of that evidence given that alternative or the defense hypothesis. There'll be more talk about propositions in the following presentation, so I know Stephen is planning to talk about that coming up soon. The formulation of propositions can be challenging in some cases, and I'm not going to mention a whole lot about this, but usually as a scientist we try to base this on relevant information, so things like if they're consensual partners, If it's a vaginal swab from the victim, then that's information that can be quite useful in formulating your propositions. Typically, we ignore, or we really do not want to use any type of irrelevant information like motive or prior convictions. The evidence from the ballistics report, the evidence from other disciplines. Again, these are things that are sort of outside of our view as a DNA scientist and a DNA analyst, and looking more toward the responsibility of the judge and jury to evaluate those kind of details. So I'm just going to mention this again. The likelihood ratio is the probability of observing the DNA typing results. Notice it's the same in both the numerator and the denominator. We're talking about the same piece of evidence given or if we have one proposition that's true, typically called the prosecution's proposition, versus the defense proposition is true. Now, when we talk about the values that we may observe when we assign a likelihood ratio, if we have a likelihood ratio that is 1, a likelihood ratio of 1 basically means the DNA typing results are just as probable if the prosecution's proposition is true than if the defense proposition is true. Think about this like a seesaw. If you have two people that are equally weighted on a seesaw, then it's perfectly balanced, and so it's not weighing in one direction or the other. Once that likelihood ratio grows above 1, you now start to favor the explanation from the prosecution's hypothesis has a better explanation of the data than the defense hypothesis. So any likelihood ratios greater than 1 that can get large, up to the cajillions, whatever number you may have, that is evidence that is in the favor of the prosecution's hypothesis. If that value is less than 1, well, now the explanation of the evidence from the defense hypothesis is a better explanation. So again, think about our seesaw. One side is favored versus the other, and so if you have values less than 1, then that is now favoring the defense explanation, the defense hypothesis of this evidence. We have to be careful the way that we present the likelihood ratio. Now, typically in the numerator for our HP, this probability is usually 1, since in theory the prosecution would only be prosecuting this person of interest if they are 100% certain that he or she is the perpetrator. And again, this is typically the case when we talk about single source samples where there's no drop in, no drop out, and maybe in some very limited mixture examples, which we'll do one later. So usually the numerator in the HP is 1. And for the defense, because defense may be arguing that it's someone else in the population, typically we're trying to identify who else may have left this evidence. Usually you use the Hardy-Weinberg, that is the random match probability. So again, in a very, very simple explanation here of the likelihood ratio, it would reduce to 1 over the RMP. So instead of saying 1 in 100, the likelihood ratio would be 100. Now we have to be careful how we state the likelihood ratio. There's a really specific way that it needs to be said. So you would report something like this: the evidence is 1 million times more likely to be observed if it originated from Mr. Smith rather than if it originated from an unknown, unrelated individual at random in the population. We have to be careful because what we've just stated here is actually we have verbalized that math that we see in the likelihood ratio, because we talked about the evidence and then we talked about the propositions. If it originated from Mr. Smith, that's the prosecution, versus if it originated from an unknown. That if is a key word to let people know that you're talking about different propositions. It would be inappropriate to say something like this: it's 1 million times more likely Mr. Smith left the evidence rather than an unknown, unrelated individual. Now, in this case, what we've done is we've actually went from presenting a likelihood ratio to now presenting a posterior probability. And so we need to be careful that we don't what we call transpose the conditionals here. So you can always be safe if you remember to first talk about the evidence and then use the words if when you're talking about the propositions, and that will help you to avoid this trap. Dr. Buckleton told me this story. I guess a colleague of his, Stella McCrossan at the FSS, would have this sort of spotting trick where if she didn't hear the word if when someone was repeating the likelihood ratio, she would make that correction. As we mentioned, we have to be careful when we're presenting the likelihood ratios, whether in court or in your reports, that we don't transpose the conditional. Again, if you're talking about the probability of the evidence given a proposition, that's okay. You're good. You're on solid ground. But if you switch that and you talk about the probability of the proposition given the evidence, then that's not correct. And Dr. Gill mentioned this again last week. So we have to be careful the way we make sure that we present the likelihood ratios correctly. The last thing I want to mention is the likelihood ratio, notice, is not a probability. It's actually a ratio of two probabilities. So the final calculation, the number that you give, is not a probability of, say, that the person of interest left the evidence. It has nothing to do with the probability of guilt or innocence. It's just simply a calculation where you're comparing the strength of two or more different hypotheses given the evidence profile that's present. So be careful, because we're used to doing CPIs and RMPs in which we're making probability statements. Likelihood ratio, it's evaluating the probabilities, but it's looking at a ratio of two probabilities. So we be careful that we understand that the likelihood ratio itself is not a probability. So what I'd like to do for the last bit here, and before we finish up, is to do some hands-on exercises with LRs to sort of get you comfortable and familiar, if you've never done likelihood ratios before, how you would actually assign a likelihood ratio given the scenario that I'm going to present. So what I'm going to do is I'm going to give you one example where we'll kind of walk through. And again, Josh has assured me that you will have the link to the handout. So let's go through the first exercise. And this is a single source sample, a heterozygote. So we have a complainant, Miss Doe, who alleges that she was sexually assaulted by an unidentified male on her way home from work. And the male was identified by a witness. He was identified as Mr. John Green. He states that he was out of town when this happened, that it was not him. Now, we don't have any biological evidence here, but we do have a cigarette butt that was recovered from the scene. So that's what we're testing. So here's the evidence. Here's my electropharogram, my hypothetical electropharogram. Everything's above stochastic. Everything looks good. Mr. Green is a 1213 reference. The evidence which we've tested and evaluated is a 1213. I'm giving you some allele frequency information here. For my propositions for the prosecution, I would say a sensible proposition here is that the DNA originated from Mr. Green. And by the way, we've looked across the entire profile. We're not just doing one locus out of the blue. We've evaluated the entire evidence and then compared to the evidence, compared to the reference, and we could not exclude Mr. Green. For the defense, we would say the DNA originated from an unknown individual unrelated to Mr. Green. I'm giving you a little bit of information here, but the way we would calculate our likelihood ratio is, again, for the prosecution's hypothesis here, the probability of the evidence, given that proposition that this is Mr. Green, that is a probability of 1. Remember, first law of probability, probabilities range from 0 to 1. So 1 is certainty that it is Mr. Green. We can say that because all of the evidence is explained by the presence of Mr. Green. For the defense hypothesis, we would argue that it's not Mr. Green, that it's someone else in the population, and that someone else would be a Hardy-Weinberg 2PQ in this case of someone that has a 1213 genotype. So using the product rule, we would multiply 2PQ, and our likelihood ratio would be 8.9. So just to, when you get a value like this, 8.9, because there's always uncertainty in allele frequencies and things like that, let's just truncate anything after the decimal. We will just chop off. So what we would then report is something like this. The evidence is 8 times more likely at this one locus. The evidence is 8 times more likely to be observed if it originated from Mr. Green rather than if it originated from another unrelated individual at random in the population. Now for you are going to do D13. So in the next week or so, take some time and calculate the likelihood ratio. I'd like for you to tell me your propositions and then calculate your likelihood ratio and then give me your report. What would you report? Since Dr. Balding talked about the Balding and Nichols formula, which is also known as NRC2, recommendation 4.2, and formulas 4.10a for homozygotes and 4.10b. So again, this is, as Dr. Balding mentioned, what's the probability of observing an individual with an AA genotype given I've already seen someone in the population with the AA genotype. So this is a sort of subpopulation correction formula using theta. So let's take a look at our example 1, but this time, so it's the same exact example, but this time we're going to use the Balding and Nichols correction for a heterozygote. So again, typically right now, most labs in the U.S. that haven't moved to a probabilistic software are using the NRC2 recommendation 4.1, which only corrects for inbreeding, if you will, for homozygotes. The Balding and Nichols or formula recommendation 4.2 will correct for co-ancestry and inbreeding. So we would use this formula, so substitute in the allele frequencies using a theta of 1%, and you can see the difference in the likelihood ratio is now 8.6, which is slightly lower than what we calculated just using the heterozygote formula for Hardy-Weinberg 2PQ. So again, I will report this as the evidence is 8 times more likely to be observed if it originated from Mr. Green rather than if it had originated from another unrelated individual at random in the population. So you do this for your exercise. So take the same information for D13 and calculate the same the likelihood ratio for correcting using the Balding and Nichols formula. Next, we'll show an example with a mixture. So again, we'll follow the Clayton rules when we're looking at mixtures. Is it a mixture? So this is a kind of interpretation that you would do normally with a mixture where you identify the artifacts. Is this stutter? Is this pull-up? Try to determine a sensible number of contributors. Again, peak-height ratios and the number of alleles that you see may help in that aspect. Determine the approximate mixture ratio. So if you have a major minor, if it's a 50-50, so try to determine the mixture ratio across the profile. That could help potentially with identifying if you may have degradation in the profile. Consider all possible genotypes and then potentially try to restrict all of those genotype combinations using peak-height ratios and mixture ratios in steps 4. And then when you're finished, compare to your reference. And then I added a step 7 to the Clayton paper just to sort of say now is when you do your statistical analysis once you've finished all of this. So let's go back to our example 1, but this time Ms. Doe is sexually assaulted and there is biological evidence. So she is taken to the hospital and a sexual assault nurse examiner has collected a vaginal swab. So now we have a mixture, and here's my sort of fake electropharogram over here for D8. We have a mixture of what looks like 2 people across the entire profile, but here at D8, it looks like we have a major and a minor. Ms. Doe has a genotype of 1011, and Mr. Green is a 1314. We do have peaks that are above our stochastic, so there's no issues here. And again, this is where we have 2 heterozygotes, and if it's a 2-person mixture, we're not worried about any missing data here. So what we would do for our prosecutions proposition is now we have a 2-person mixture, our proposition changes from a single source. We would say the DNA originated from Ms. Doe and Mr. Green. And at this point, I'd like to just say, remember last week, if you were able to watch, Dr. Gill talked about this hierarchy of propositions. And usually when you have DNA and you're not sure what source the DNA is from from semen? Is it from blood? Is it from, what type of tissue is this evidence from? You typically would report something at a subsource level. So really all you can say is something like the DNA originated. But now that we have biological evidence and maybe we've done some type of serology, maybe we've actually visualized semen or sperm on a slide, now we may be able to move into a higher level and report a source level proposition, like the mixture of the sperm originated from, collected from Ms. Doe and Mr. Green, that kind of thing. So we may be able to change our proposition slightly. The thing we need to be concerned with, again, as Dr. Gill talked about, is to be careful that we're not overstating, we're not moving into a much higher level of attribution here based upon what evidence we're testing. So let's just say for here, I'm going to stay at the subsource level, but again, if I had that serology, I could change this proposition slightly. For the defense proposition, we would say the DNA originated from Ms. Doe and an unknown individual. So what would this look like? Well, for the prosecution, all of the evidence is explained fully by Ms. Doe and Mr. Green. So my likelihood ratio would be 1. That is, we are conditioning that Ms. Doe is present, that she is present in her vaginal swab. So that's a probability of 1. And, so we're going to multiply, the probability of 1 that it is Mr. Green, according to the prosecution. So again, we did our interpretation, and we cannot exclude him. So in our likelihood ratio for the numerator, this would be 1, because its evidence is fully explained as a mixture of these 2 individuals. For the defense, we are still going to condition. We're going to say that Ms. Doe is there. We expect her to be there in her vaginal swab. So that's going to be a probability of 1. And there's an unknown individual, someone who is a 1314. So we will multiply that 1 times the 2PQ, and our likelihood ratio is 8.9. Now, if you notice, that's the same likelihood ratio we got, for example, 1 in the single source, and it makes sense, and that's sort of one of the diagnostics you would do is sort of when you're looking at this is, well, it makes sense because we can fully explain the major as coming from the complainant, and then those 2 minor alleles have to be explained by this person of interest. My report would be 8 times more likely again. So you do the same thing with D13, and then again we'll report next week. So I'm going to finish the last little bit that I have. Again, the title of this talk was Unrelated and Related, and I'm just going to give sort of a general overview because my friend Sarah Noel is going to be speaking here in a couple of weeks, I guess in 3 weeks, on relatives in casework. And so she has some really interesting data that she's generated and is going to be presenting. So in this case, we're talking about the situation where maybe this person of interest says, oh, it wasn't me, it was actually maybe my brother who did this. So typically in the standard likelihood ratio, we're comparing our evidence, our observed data, our electropherograms, and we may have the reference from our person of interest, our POI. And so the comparison that we're making in sort of the standard likelihood ratio is we're saying, is it this person of interest or is it an unknown, unrelated individual in the population? And so that's what we've typically just been talking about, is how our likelihood ratio would look like this. So we're basically asking the question, is it him or could it be any unknown, unrelated individual out there in the population? When we talk about relatives, we have to change our likelihood ratio because now we're not talking about random, unrelated individuals, but we're talking about, is this a brother or a father or an uncle, some close relative of the person of interest? So notice how our likelihood ratio changes. In the defense hypothesis, it becomes the DNA originated from a relative of the person of interest. And specifically in this case, we're going to look at a brother. Now, in order to do this, we need to talk about this concept of being identical by descent. And if we're going to talk about siblings, we would say that siblings can share 0, 1, or 2 alleles identical by descent. So this is how this can happen. So let's say these two parents over here, who are AB and CD, and they could have any one of 4 children with the 4 genotypes that we've outlined here. So let's say their first child is an AC genotype. And then sometime later, these two parents decide to have another child. So the second child they have may have also the AC genotype at this locus. And if that's the case, then these two brothers share 2 alleles identical by descent. And what that means is both of these brothers got the same A from the first parent and the same C from the second parent. So both of their alleles are identical by descent. So they are the exact same alleles. Now, it's possible if the first brother, if the first child is an AC, and then the second child is a BC, well, now these two brothers only share one allele, that is, the C, is identical by descent. The A and the B are different. It's also possible that if that second child is an AD, again, these two siblings would share only one allele identical by descent. The A, the C, and D are completely different. They're not even the same. And finally, if that second child is a BD, well, now these two siblings have no alleles that are identical by descent. They are completely different from one another. And there is this one chance that they would be have 0 alleles identical by descent. So about here, 1/4 of the time, you would expect that 2 brothers, or a brother and a sister, or 2 sisters, about 1/4 of the time would have 0 alleles identical by descent. About half the time here, they would have 1 allele identical by descent, and about 1/4 of the time, they would have 2 alleles. And I'm saying about because, you know, mutations can occur, but we'll just say here, this is the sort of what we expect when we have siblings. 1/4 of the time, 0 alleles identical by descent. Half of the time, 1 allele identical by descent, and 1/4 of the time, 2 alleles identical by descent. So we call these kinship coefficients, and I'm using the letter Z here to represent the kinship coefficient of having 0 alleles identical by descent. We calculated this to be 1/4. Siblings having 1 allele identical by descent is 1/2 of the time, and 2 alleles 1/4 of the time. So you can see here for parents, you expect that a parent will have 1 allele identical by descent with their child, and you would expect 0 for 2 and 0 for 0 alleles, IBD. So we're going to use these kinship coefficients for calculating our likelihood ratio for a relative, in this case, a sibling. Now, if the 2 siblings have an allele that is not identical by descent, then we're going to use the frequency of that allele in the population as part of our calculation. So let's look at example 5, which again is a rehash of example 1, where we have the sexual assault, but we're using the cigarette butt, and we have a beautiful profile, no dropout here. Mr. Green is a 12-13, and he has alleged here, look, It wasn't me, it was my brother. So for the prosecution, nothing has changed. The prosecution still believes here this proposition is that the DNA is from Mr. Green, and so we can explain all of this evidence. The probability there of my numerator would be 1. But for the defense, the argument is it wasn't Mr. Green, it was maybe a brother. Well, do you have a reference that we could test? No, I don't. Okay, so our job now is to calculate this for our HD, or for our denominator. The probability of having a sibling who is a 1213, given that our person of interest is also a 1213 and that they are brothers. So we have to consider all the different ways that siblings could share 12s and 13s here and have the same profile. So I have a chart here we're going to fill in, and we're going to go through and look at each one of these kinship coefficients, 2 alleles identical by descent, 1 allele, that is the 12, the other 1 allele, which is the 13, and then no alleles identical by descent. So the first question is it possible for you to have a sibling who is a 1213 and another sibling here, our person of interest, is also a 1213, and they have both of these alleles are identical by descent? Remember, this happens 1/4 of the time. So yes, it is possible that we can have a 1213 sibling who shares the same 12 and 13 with his other sibling. So that probability is 1, and we talked about that earlier. Next, we're going to focus only on the 12. Is it possible that the 12s are identical by descent and nothing else? Well, yes. If, say, for example, the mother has this red 12, she gives it to her first child, and then the second child is a 1213. Notice these two kids here in this red blue and red purple both have the 1213, but only the 12 is identical by descent. They both got that 12 from, say, mom, but the 13s they have, although they look like they're the same, are actually different 13s. So if they are not identical by descent, remember we're going to use the frequency of that 13 allele as part of our calculation. Next, we fill in for the 13 being identical by descent. And again, this is just like the example with the 12. Yes, they could get the same 13 from one parent, but the 12s could be different. That is, they could be not identical by descent, so we use the frequency of the 12. And then finally, is it possible that these two brothers have the 1213 genotype, but neither of these are identical by descent? Well, yes. Let's say this first brother is this 1213, red-blue, and the second brother is this 1213, black-purple. They're both 1213, but neither of these 12s or 13s are identical by descent. So since there are two different ways that you can get this, we're going to use the frequency of the 12 and the frequency of the 13. Since these are not identical by descent, and there are two different ways to do this, our formula would be basically 2PQ. So what we're going to do is we're going to multiply across, multiply our probability here of the kinship coefficient, time this probability here, so we'll get the product across, and then we will add down, because it could be this, or this, or this, or this. So we're going to add these, and this will become the formula that we will use in our HD for the proposition of having a sibling who has the same genotype, but they are not identical by descent. So when you plug in your allele frequencies using this formula and you calculate it out, notice our likelihood ratio is 2.5. And we said this was a random, unrelated individual. Remember, it was 8.9. So you can see the effect on the likelihood ratio when you are considering a relative and not just a random person. So we would report the evidence is 2 times more likely to be observed if it originated from Mr. Green rather than if it originated from a full brother of Mr. Green. You have your example. I want you to do the D13, and I've given you a chart So fill in your chart, calculate your formula, and then report. So to finish up, the probabilistic methods of interpretation, I feel, make better use of data compared to older methods that we've been using. Not to say that these other methods are incorrect or there's something wrong. There's nothing, absolutely nothing wrong with CPI or RMP. As long as you're applying it correctly, you're using your thresholds and all that stuff, you're fine. The probabilistic methods, I think, make better use of the data, and so they're much more efficient, and I think that's one reason why many, many labs are moving in that direction and have moved. And again, the first requirement is to move from, again, using thresholds and this binary approach to using likelihood ratios and a probabilistic approach. And I like to use this little example. If you've been standing out here on your binary rock, you need to sort of move to the ProbGen rock, but the first step really is to move from binary methods, again, not to say that you can't use likelihood ratios for binary methods, but if you've never done likelihood ratios before, that's the first rock you kind of need to jump on before you jump over here to the ProbGen. And sometimes, again, because people have this fear of likelihood ratios, they may feel like that rock is way out here, but it's really not. I think once you start getting into feeling more comfortable using likelihood ratios, then this is a much easier task ahead of you. So I'd like to thank Josh and Tamara especially, and again, Brian and Stephen and Simone and Dr. Buckleton, and also my co-author on this presentation, which I didn't mention up front, but I would like to really mention that Joe Bright and I I've had the pleasure of working with Joe the last few years. We've been doing several workshops, and it's been a real pleasure working with Joe. And I'd like to thank, again, NIJ and the Forensic Technology Center of Excellence and RTI for hosting this webcast. Thank you very much.
Thank you so much, Mike. That was a fantastic presentation. And Mike, you're going to be back in 2 weeks for our next session to go over the results of the competition. Correct? Okay. And Mike's going to be speaking as well in our next webinar. One thing to note is, as you see in the presentations we've seen so far, there's some redundancy in the presentation of the information, and that's intentional. We're hoping to share a lot of the information multiple times, different presenters, and help us on our learning curve. So thanks so much, Mike. That was great. Next, we're going to be moving on to Stephen Myers. So Stephen, go ahead and take it away. Thank you.
Actually, I thought we were going to take a quick break for people.
You are absolutely right, Mike. I'm sorry, Stephen. Let's see, it's 2:05 now, and we were going to take a 5-minute break, and we'll be back at 2:10. Thank you. Okay, welcome back. We're ready to resume, and I introduce Stephen Myers to present our next lecture.
Stephen, you might be muted.
Never fails. The light's blinking at me and I ignored it. I just wanted to say initially that I want to thank Tamara especially for pulling this all together. It was a huge effort, and I hope it was worth it for the community. Certainly, I think it will be. Also wanted to thank Josh and RTI for everything they're doing making this happen. My part on this today is trying to kind of bring this to a boots on the ground kind of practical level for a bit, and talk about the propositions that are being used in casework today. Some of the things that we can think about, and towards the second half of the talk, get a little aspirational. Some things that are being done, in our lab certainly. But also, I would love to see expanded, and they all feed off of things that you've already heard about. The suggested reading I put out is this practical guide for the formulation of propositions that was published in JFS. I would also suggest people take a look at this draft document. So this was a document created in the OSAC. It was submitted to ASB as a proposed standard, and it's about assigning propositions for likelihood ratios. It has already gone out for open comment in the ASB realm, and I believe now it's going to be, there'll be adjudicating comments. Between the two of these, I was involved in both of these documents, and I learned so much by being involved in them. And I think, and hope that if people give them a good reading, it'll not only, they'll give you a good foundation, but give you a lot to think about in this topic. So this particular talk, we've talked a lot about the hierarchy of propositions and where different parts of our testimony could go. This talk, we're just going to really be sticking to that subsource level. Just really talking about the proposition setting that criminalists are setting when they're using their probabilistic genotyping software, and they're coming up with those LRs for their reports and for testimony. Now, propositions, the LRs may seem like a foreign thing to a lot of people. And again, as Mike said, especially for people who have not been doing kinship. But it really shouldn't be that foreign, because the concepts that we're dealing with really were already there in the various, frequentist statistics that we were reporting before. Because what are we talking about? We've got generally, and it's all generalities, but generally we've got someone who is being accused of a crime, and with the evidence, they're generally saying that they're not the contributor. And so what has our stat been? It's been about the probability of seeing that evidence profile given some unknown person who is not the contributor, and generally, most often, some unknown, unrelated person. So not related to the person of interest, not their brother, not their father, whatever. So, maybe your lab, reported, or if you're an attorney, maybe the lab that you used was reporting combined probabilities of inclusion. Again, a statement like approximately 1 in a gajillion, whatever, random unrelated people would be included as a contributor. There's a proposition there, a random unrelated person. Maybe you were or worked with a random match probability lab. We've got a couple more elements to the proposition there. We've got, an assumption about a number of contributors. We may have an assumption about who one of those contributors is. But again, for the people who we aren't assuming, we have this random unrelated person. So propositions have been part of our stat all along. We didn't necessarily always think about them in those terms, though. Keep pushing the wrong button to go forward. So, with probabilistic genotyping, as was said, this is all about likelihood ratios now. We're no longer doing our standard, RMP or CPI. So LR, I can go through these quickly. Mike did such a great job. LR is likelihood ratio for our quantifiable testable evidence. So again, I'm at that subsource level, the DNA, so our quantifiable testable things. The evidence for us is that DNA profile. PR, it's probability. It's a conditional probability. We've got that vertical bar, that if or given that bar, a probability of seeing that evidence under two competing propositions. So they need to be different propositions. They need to be mutually exclusive propositions. They can't both be correct at the same time. So I'm going to use the phrase H1 and H2. I personally generally am not bothered by HP and HD, but I know there are people who are very bothered by those. So maybe dialing down some of the concern for this talk, I'll stick to H1 and H2. But we are still generally dealing with that in most cases, H1 is the prosecution's theory or proposition of who the contributors to this evidence are. And in general, H2, if not the actual defense theory, is at least a surrogate for the defense theory. It's one reasonable proposition that's being put forth that would be in line with, what could be considered to be a defense position. So I here is that relevant case information. So Mike talked a bit about that. So, I'm a very visual person. So, if it helps at all, I kind of always like to think about things visually and see them. And so if we think about a likelihood ratio, trying to always keep in mind that we're talking about the probability of an outcome. So for us, the probability of seeing the DNA profile. That outcome does not change whether you're in the numerator or the denominator. It's the exact same outcome. It's just we're figuring out, well, how probable is it you would have gotten there under two different ways that you could approach it. So, the probability of finishing, I'm not saying winning, but finishing the San Francisco Marathon, if you did a 20-week team and training preparation, really ate right, did everything right. So the probability of getting to that outcome, if you did all that work, versus the probability of that same exact outcome if you sat on the couch and played video games for 20 weeks. I think most people could figure and see that the probability of getting to that outcome is higher under the numerator proposition, effectively, the numerator way of training versus the denominator. And so, when we've got this ratio of probabilities, we have to remember the numerator probability does not provide support for or against the numerator proposition. The denominator probability doesn't provide support for or against the denominator proposition. But the ratio of the two does provide support for one proposition or the other. So if that ratio is greater than 1, then that LR supports that first proposition. If it's less than 1, the LR supports the second proposition. And if the LR equals 1, magically nails right on 1, then basically both propositions are equally supported by the LR. The probability of seeing the evidence could be high under both propositions. It could be low under both propositions. But those probabilities are equal. So effectively, it's a push. After testing the evidence and looking at the probability of getting this evidence, using these two probabilities, they really don't tell you anything to push you one direction or the other. Now, what propositions are we going to assign? Everyone's been talking about different propositions will lead to different probabilities. The thing that follows from that, of course, is that different proposition pairs will lead to different likelihood ratios. There's been like some fear in the community about having different numbers presented and that this might confuse people. I think we need to embrace it. We expect that if you say, well, the way you get there is going to change, then why would we expect the probability of getting there to be the same? What we need to do is we need to embrace explaining to people how these propositions are affecting the probabilities, and that we expect differences to lead to differences. We are going to have some assumptions we have to make. We are going to have to, for the softwares that we're dealing with, we're going to have to generally, not always, but generally for most of these softwares, come up with a number of contributors. We're going to think about who can be assumed, as has been talked about now a couple times. We're going to have to think maybe about relatedness between contributors. And then, as Dr. Balding was talking about, there's the population group and substructure. What allele frequency database are you going to use? What level of substructure? Now, again, to maybe not have this feel so unfamiliar, especially if you were an RMP lab doing mixtures, a random match probability lab that was doing mixture interpretation, assuming a number of contributors, et cetera. Most of these things have already been part of our decisions. These aren't things that are new and novel just because we're doing a likelihood ratio. The transition really isn't as far maybe as you might have thought. The nice thing, though, is that automation is making this all a lot easier and a lot faster and hopefully a lot more consistent. But, we are having to go through all this discussion about this to get people's heads into it, but I'd like to maybe hope that you can see that a lot of what we're talking about is not that different. We've already been talking about the probability of seeing that evidence profile given a particular proposition. Now we're just stating, well, here are two reasonable propositions. Let's look at the ratio of those two probabilities. Now, when you're dealing with propositions in casework, they're kind of two separate phases. And maybe some people wouldn't have thought of this. I mean, I'd never put it in quite this way before this talk. But the softwares that we're dealing with in general need one set of propositions for the interpretation phase, and then you're going to augment those propositions for the LR phase. So when we're interpreting the evidence for the genotypes of people who could have been the contributors, first off, we're going to do this without any knowledge or reference to a question person's DNA profile. We're not going to say, okay, well, this is our person of interest, this is our suspect. I'm going to base the interpretation upon their genotype. We're not going to do that. None of these software programs do that. If you think they do, that's not correct. So it's really going to be this kind of blind look at the evidence. Now, they are generally going to assume a particular number of contributors. So really, we're kind of dealing with one proposition for the numerator and denominator, if you could think of it that way. If you were to calculate an LR at this stage, it would always be one because the propositions would always be the same for the software programs that we're dealing with. Now, if there is ambiguity regarding the number of contributors, you might do multiple interpretations. And again, now there's some software programs that will allow for some, maybe a different number of contributors in the numerator than in the denominator. But even there, you're still dealing with not assuming the person of interest. Now, those propositions, you could incorporate the profiles of reasonably assumed people. So, we talk about the victim on her vaginal swab, consensual partners, suspect on his underwear. I'll talk about these again in a second just to kind of drive the points home. Regular driver of a car and their steering wheel. That's someone who might be reasonably assumed to be present in the DNA profile of a swabbing of that steering wheel. So if you had, for example, also someone who is known to just generally have direct contact, someone handed you something, well, again, that might be someone you might consider. When you're selecting the number of contributors, now, not going to go into a whole, here's how you pick the number of contributors. That is at least a lecture in itself, probably. But I will bring up the one point that once you assume people, that initial assessment of the number of contributors that you might have just looking at the evidence profile itself, once you have an assumed contributor, someone who you're saying is definitely there, that might actually change things. So in the example on the left, and this looks an awful lot like the exact same peak heights Mike was using. In general, this looks like a two-person mixture, and if you had an assumed contributor who had those first two big alleles, then you've got two nice evenly height second lower alleles there. This looks like a two-person mixture. If, however, your assumed contributor actually was a homozygote at the 8 allele, so they only have this 8 allele here. Well, now looking at this, we've got 1, 2, 3 additional alleles. These other peaks are consistent with being stutter peaks. Could be additional alleles, but in general, if they're consistent with being stutter, we're generally going to not think about those for the number of contributors over a course of a whole profile. But in this case, we've got 3 clear alleles that are foreign to this assumed contributor, and so we must have at least 3 people. So this interpretation, and you of course look at the entire profile, but it would proceed as 3, given that we've got this assumed donor. Now the next phase is where we're actually going to be calculating our LRs. So the propositions for our LRs, we're going to have to update things to now include our question persons of interest, our suspects, and sometimes, our victims, depending on the case, as I'll talk about later. Now, for this, we have to have 2 separate propositions. They have to be mutually exclusive. They can't be the same. Now, one of those propositions is going to assume 1 person of interest. If there are multiple, it might assume multiple. And so, if you had a 3-person mix, it could be 1 person of interest, 2 persons of interest, or 3 persons of interest, all included in that one proposition. But at least some of those will not be included in the other proposition. That's how we get this difference. So at this point, we can also think about relationships of unknowns to the profile people. The most typical kind of starting point and what you're probably going to be putting in your reports or seeing in your reports if you're an attorney or a law enforcement person, typically it's going to assume unrelated. Now, Dr. Buckleton may talk about a stat that is available in StarMix that actually incorporates unrelated and related all into one stat. But typically what you're going to see is an assumption of unrelatedness. And again, at this point, because we're calculating likelihood ratios, if you've got an unknown, untested person, well, to account for them, you're going to have to bring in allele frequencies or probabilities and population substructure elements. So that's where those formula now come in. So in most labs, in most cases, I would say probably the typical approach that is used most commonly, that if you've got some particular number of contributors in, and there are X contributors that are reasonably assumed, and that X could be 0. It might be no reasonably assumed people. For the interpretation phase, it's going to assume that, a particular number of unknowns, subtracting out however many assumed individuals you have. That's going to be just the general proposition for the interpretation phase. For the LR phase, most often, one of those unknowns in the numerator would be switched out for our person of interest. And in the denominator, it would just stay all unknowns except for any assumed individual. Now, the beauty of this is that it's really simple and it's easy to apply consistently. You can have everyone in your lab doing the same thing. And in most cases, this is completely sufficient. Again, setting the stage a little bit, there are other cases where it might not actually represent the assertions that are going to be presented in court. And in general, if the jury is meant to assess a particular assertion, it would be good to hear the probability of the evidence under that assertion and under whatever alternate assertion. So for example, I mean, is your stat relevant? If in the numerator you had the proposition that it was, the suspect, and in the denominator you had the proposition that it was unrelated, if the entire defense was that it was actually the uncle. So, what you really needed was the probability of the evidence given that it's the uncle of the person who's on, who's the defendant. So again, most of the time, this standard scenario is fine, but there are alternate situations where it may not represent what's actually being, what the triers of fact are being told to evaluate. Now, just in general, some people would stop at this simple one, but other people or agencies might actually go farther than this. So, super simple case. Say you had a break-in in a house, and amazingly, your local police agency is not so busy that they can actually come out and work a break-in at your house, rather than telling you to come in and file a report. And they look at the window and they see a nice blood stain on the window. Certainly, you look at the DNA results in this, and they show a nice single source contributor. If you really wanted to be thorough, you could test the residents to rule them out to make sure it wasn't them. But the typical propositions, what would usually be done? You'd enter into your software that you have one unknown person, and it would do its interpretation under the assumption of just one person. But for that LR phase in the numerator proposition, you're going to say, well, the probability of seeing this evidence given it's the suspect. And in the denominator, probability of seeing this evidence given it's one unknown, unrelated person. So again, without any reason to think about a relative, this is a reasonable proposition pair. And generally, that's the end of it. Pretty simple, basic case. Also simple, we've talked about vaginal swabs, and we've talked about these ones where you might have a situation where your DNA results, just looking at them, look like two contributors, and the victim or non-sperm fraction DNA profile could easily account for one of those contributors. So the victim and one unknown person could account for everything. So I would argue, in general, the victim's presence is usually not in contention. This is a swabbing from her vagina, so having her DNA on the swab, not really a contentious issue there. So what would our typical propositions be for the interpretation phase? Victim and one unknown. For the LR phase, not surprisingly, victim and suspect, and denominator, again, victim and one unknown, unrelated person. And really here, that unknown, unrelated person is really unrelated to both of them. Because as Mike just demonstrated, if you have someone and you're saying, well, what's the probability some untested relative of theirs has a particular genotype? Well, the person you have tells you something about the possible types of that untested person. And so really, the probability of the genotype for this unknown, untested person would be affected by them being a relative of the victim or the suspect, or depending upon their relationship, both. But again, without reason to suspect a relative, as this unknown alternate, usually we just stop at that simple proposition pair. Now, if there's a little twist here, and you've added in an extra contributor, the results in that DNA mixture look like 3 contributors, but it's seen that, well, the victim, maybe in the information that you got about the case is that the victim had had consensual intercourse. And so you can get the profiles of not just the victim, but the consensual partner. And, looking at those in comparison to the DNA results, you could see that, yes, this looks like it's these two people plus an additional contributor. So most agencies, I think, would still be okay with saying that that consensual partner can be reasonably assumed. Now, there are agencies that would really want to always back that up by running what might be called a preliminary LR. So in the preliminary LR, you'd interpret it as a three-person mix with the victim and two unknowns, not assume that consensual partner. And then for the LR phase, the consensual partner would act as a person of interest, effectively. Victim and partner and one unknown over victim and two unknowns. That would be your proposition pair. And if the ratio of the two probabilities of seeing that evidence was greater than 1, that would provide support for that first hypothesis. And then the agency would typically go on to now assume that person, incorporate them as an assumed person in both propositions. So this second set, we have to now go back and reinterpret the evidence. We can't use that original interpretation now, given most of the software programs that are out there. So this would be victim and partner, and one unknown would be the interpretation phase. And then when we got to that LR phase, the unknown from the interpretation phase, well, in the numerator proposition, it would be your suspect, the denominator, this one unknown, unrelated person. Now, there is sometimes some disagreement over, especially in court, can happen over whether it's okay to assume the partner. So, what could happen? You certainly could do the victim, the suspect and one unknown as the numerator proposition, and the victim and two unknowns. And it would lower the LR, but is that actually matching what the prosecutor's assertion is? The prosecutor has asserted that part of that profile is this consensual partner. So now you'd be doing an LR that's not actually representing what the jury is hearing. So that's a little problematic. You could do victim plus partner plus suspect over victim plus two unknowns. The prosecutor was saying, no, they're all three there, and the defense is saying, no, it's the victim and two unknown people. Well, that's going to really increase your LR, because now you've taken someone who really just should be assumed and said, no, they're an unknown person. And what happens when you have an unknown person? Well, now you have to bring in the probability of seeing that unknown person's genotype. And that's going to make the denominator probability rarer, which is generally going to drive up the likelihood ratio. So in general, I think you can get my sense of where I think things should be. In a situation like this, you would assume both the victim and the partner in both propositions. Now, the person you're going to assume is not always, the victim in a case. The POI is not always the defendant. So if you had a case where sexual assault was alleged and you have the suspect's underwear from a suspect kit and a mixture was observed consistent with two contributors, part of that information that you have from the case that is relevant is, where was the item collected, who is who's in regular contact with it, what's the direction of transfer. In this case, this direction of transfer that's alleged is the victim's DNA onto this underwear. The suspect can be reasonably assumed to be on his own underwear, and that's rarely in contention. So again, our interpretation phase for this would assume the suspect in the proposition for the software. And the LR phase, we would assume the prosecution's proposition is, of course, going to be the suspect and the victim, because if the victim's not there, then this evidence has no meaning for the case. And the alternate proposition would generally be suspect and one unknown unrelated person. So now we're going to get where we're a little aspirational on my part on where I'd like to see the community going more. So let's say now that a knife has been found. So there's a victim who has been stabbed to death. This knife is not found sticking out of the victim. If it was, we could just reasonably assume the victim's presence. Instead, it's found somewhere away from the victim. It's also not in the possession. It's not being held in the hand of the suspect. How would we deal with this now? So let's say we look at the stain results, and this suggests 2 contributors. Now, without looking at either person, just thinking about the information we have, and we've got information, we've got a 2-contributor mixture. Who could reasonably be presumed to be contributors to that mixture? Can we think about that? Think about it for a second, what the propositions might be for that. Well, so 4 of them that come up really quickly are, well, it could be that the decedent and the suspect are both contributors to that mixture. Now, remember, at this point, we haven't actually looked at any of the profiles in comparison to the evidence. So just thinking about, I've got 2 people here, well, maybe both are contributors to the mixture. Alternately, maybe neither are contributors to the mixture. Could be that the decedent is a contributor, but the other person is some unknown, unrelated person. Alternately, the suspect could be a contributor, and the other contributor is an unknown, unrelated person. So all of those are reasonable propositions that could explain this evidence, not ever having even looked at how their profiles compare to it. Now, I'm going to go through the example using this victim and suspect kind of situation. This same general concept, though, applies if you have 2 suspects. Could be suspect 1 and suspect 2. Could be neither. It could be suspect 1 and an unknown person. It could be suspect 2 and an unknown person. Those are all reasonable explanations for how you could have gotten a 2-person mixture in that stain. So typically, a lot of labs would do simplified propositions. I think most agencies at this point would do this. So the interpretation phase, they would just have 2 unknowns, because this item was not found, again, sticking out of the victim, so there are no reasonably assumed people here. Now, for that phase 2 LR, I'd say most labs, from conversations I've had, and also some programs out there only would have this capability, they would do each person separately. So that H3 proposition I had, the probability of seeing this 2-person mix if it was the decedent and 1 unknown person, and for the alternate proposition, they would say 2 unknowns. And that would be the LR just looking at the decedent, the weight of evidence assigned to the decedent. For phase 2, for the weight of evidence assigned to the suspect, they would say the suspect and 1 unknown unrelated person, and the alternate proposition would be 2 unknown unrelated. So again, I think that's the most typical. Now, another common one would be a compound proposition pair. So this is not universally done. There are labs who don't do this, but I think it's pretty common. Again, the interpretation would be done with no assumed individuals. But the LR phase, the first proposition would have both people there, and the second proposition would be neither person there. So it's all or nothing. And I would say that there is a split on which of these LRs would actually get reported. I think most labs would report that simplified LRs, so the one just, where the numerator just had the decedent, the other one where the numerator just had the suspect. Some labs, from my understanding, do only report the compound LR because they feel this best represents, the evidence at hand and the questions. that could be out there. So some of the things to think about, though, those simple LRs, I would say they don't really represent the version of events that you probably are going to be hearing if you're a trier of fact in that courtroom. So think about it. That first one where it was the decedent and one unknown person, well, that proposition specifically assumes, the one where it's the suspect and an unknown person. That one specifically assumes that the decedent is not there. And so if you're assuming the decedent is actually not part of that mixture, and in neither proposition, then what does this knife have to do with the crime? You have no connection whatsoever between this and the murder. On the other hand, if you only assume the decedent and not the suspect in that numerator proposition, then you're assuming the suspect is not actually there. And if the suspect's not there, well, it may be the murder weapon, but you've got nothing connecting this the suspect to that murder weapon. So by just focusing on one or the other and in the numerator proposition and not including both, in this particular case, you've kind of disconnected certainly this suspect with this crime, or this item of evidence with this crime. So that has an issue because, again, it's those stats would not necessarily be fully representing the probabilities that the jury is being asked to assess. But say we did that last compound LR, where it's first proposition is both of them, the other is that it's neither. You're going to see some really big LRs out of this. I mean, 10 to the 60. I mean, kind of crazy big. The other issue with that, I mean, that's not by itself a problem, but the other issue is that if you're dealing with like a major minor mixture, say even one of the contributors is very low level, possibly even would have to require dropout, you might still get a really big LR, not 10 to the 60, but a really big LR. And that same weight of evidence statement would be effectively used for both contributors, even though that minor donor really is a lot more uncertain. So is there some way we could take care of all these issues? So first off, just in those proposed standards, remember I said that not every lab would do the compound one. Well, in the proposed standards, it's actually directing you as a standard using the word shall, that if you've got multiple persons of interest that have LRs that support an association, so you do those simplified LRs and multiple people give LRs greater than one, then you shall perform a proposition pair, one of those compound calculations that tests whether those multiple people can be included together. So, you got a great LR using the simplified one for the decedent. You got a great LR using the simplified, proposition for the suspect. But if you put them together, if it's a zero all of a sudden, if together they cannot explain that evidence, people need to know that. And so there's an actual direction to do that. Now, on the flip side, a recommendation, not a standard, but a recommendation is that you actually report simplified values, though, that you make sure that those are out there and available to everyone. And so, it doesn't dictate how you come up with the simplified one, but you want to get the weighting of evidence established and reported for the individuals, not just for the pairing. So an alternate way that an LR could be created that kind of satisfies all of the concerns I've expressed about those super simplified calculations is, well, we've got to kind of start over. So it may be that the defense is more than willing to concede the presence of the decedent. I mean, you've got someone who's stabbed to death, you've got a knife found, you know, in the vicinity, you know, with blood on it. Maybe say, okay, yeah, that's the murder weapon, but it's not the defendant's blood. He's not part of that mixture. So prosecutor is probably still going to be arguing for both, though, because for all the same reasons I've already stated. So in this one, your interpretation phase, you're going to have to reinterpret this, assuming the decedent as one of the contributors. And for the LR phase, your propositions would have both of them in the numerator and the decedent and an unknown in the denominator. Now, alternately, maybe the defense would concede that there's an innocent reason that the suspect's blood is on that knife. You know, it's a park. Maybe there's barbecues there. The person says, hey, you know, yeah, that's one of my knives. I cut myself, you know, barbecuing over there, and, you know, in all the flurry, I must have left the knife there. But, you know, that is not the decedent's blood. That's just my blood on there. I don't know whose other blood that is. Could be argued. Now you'd again have to circle back and reinterpret, assuming the suspect. In our phase 2LR, again, the prosecutor generally going to be arguing for both. That alternate proposition now would be the suspect and one unknown. Now, I will say, though, if this line of argument had been taken and it still said, okay, yeah, I bled on it, it was there, and yeah, someone else picked it up and stabbed the victim. At that point now, we have left the subsource level and we've moved up to activity level, and hopefully you can sit back and not have to think about your DNA typing results on the witness stand. Now, you know, so what I would suggest, you know, I know that at this moment I'm still in the minority, but what Cal DOJ, my agency, is actually doing is we would actually report 3 LRs. But in our text, so we'd have a table listing 3 LRs. In our text, we would still emphasize the simplified values, but we would use those modified simplified values, not just decedent plus unknown in the numerator or suspect plus unknown. Every one of these numerators has both in there, but we've got 3 reasonable alternate propositions that we put forth, and all 3 of those then create 3 likelihood ratios. Now, this looks to a lot of people like you're doing something that you shouldn't do, because it looks like you're assuming someone who's not an intimate contributor, and we've been taught in general, you should never assume someone who's not an intimate contributor or a reasonably assumed contributor. So does this violate those rules and regs? I would argue no. The calculation may look the same, but we're doing it for a completely different reason. What we're doing here is we're saying, look, we've got this evidence. We've got 2 reasonable explanations for this evidence. We're comparing the probability of seeing that evidence given 2 reasonable, mutually exclusive explanations. Has the benefit of looking at a variety of ways you could explain the evidence. It lets you isolate each person of interest into a simplified value. And we're not just presenting one value as the likelihood ratio. You know, it would be a problem if you only presented, say, that one simplified one and never didn't assume the suspect. But we're showing a range of values, a range of proposition pairs that could lead to the evidence. So I would say there is actually no conflict. What it means, though, is that you have to think about this a little differently. You have to be thinking about what are we dealing with the probability of the evidence given a reasonable proposition, the probability of the evidence given another reasonable proposition. Now, I'm not saying it can't be cumbersome to work with this when you've got multiple, you know, say maybe 3 persons of interest or 4 persons of interest. We ended up creating, Kyle Duke especially worked on this, created this great flow chart. I am not going to go through this in detail. We do not have the time for that. But basically, this steps our people through the process given varying levels of complexity of the case, how many persons of interest, et cetera. But the kind of the end-all result is that the numerators we're generally reporting are going to have all our persons of interest who can fit together. But we'll also report, we're not going to only report that compound LR where everyone in the denominator is an unknown person. We're going to report those kind of modified, simplified ones where if, say you had 3 POIs, the numerator would be all 3 for the proposition. The denominator would be 3 separate denominator calculations. Each one would have 2 POIs assumed and 1 unknown. So we'd have a lot more numbers in our reports. If they get to be a lot, we'd put them in a table in the back so that we're not busying up the main section of the report. But what I really like about this is that it's getting across what are reasonable arguments that could be made about how that evidence could have come to be. Now, again, there are a lot of other propositions. There are all these possible relatives propositions that those calculations did not take into account. And relatives, that could be a lot of different categories. It could be parents, full sibs, half sibs, etc. So there are a lot of things there. There are also alternate contributors. So we've always been dealing with this. It's some random untested unknown person. Well, maybe someone else is being put forth as the alternate that we do have a profile for. So you could have an LR where it's decedent plus a person of interest plus, as the numerator proposition, the denominator is decedent plus some other person of interest. Maybe we have different donor numbers. Again, those are different parts of the propositions that could vary. It all comes back to what has been said multiple times now, there is no one LR. I would say, though, that we should try and simplify, especially when it comes to our initial reports. The concept of Occam's razor, your multiple competing hypotheses, generally start with the simplest one. If you go to your doctor and you've got some cold and flu symptoms, they're probably going to think cold and flu. They're probably not going to jump right to dengue fever and start testing you for that. Now, if you had case information, like, well, you traveled to the tropics, then maybe you do need to go and test all of those things. But on a first pass, I would keep things simple. So again, coming back to this practical guide, we're trying to be practical about this. Where are we going to get our information for our propositions? Now, again, as has been mentioned, typically, the agency that, if you're a government lab, typically the prosecution's proposition is going to be clear. And in fact, they have to bring their case. They have to put forth a theory on things. So that is typically clear. The defense, on the other hand, has no legal requirement whatsoever to declare a theory. They may, and if you can find that out, that's fabulous. But there's no requirement to. They can do what they want for their best defense. So what do we typically do? Well, we're trying to give as much information to the trier of fact as we can in a reasonable way. And so we're going to adopt a proxy proposition. So again, if we have either direct knowledge about the prosecution proposition or we can make a really good guess, we'll make we'll establish that. And for the defense, we'll pick a provisional proxy proposition. And then the key thing, though, is to be open to the fact that there could be alternate propositions that are of interest. It'd be great to happen before court, so you could actually really address this. Oftentimes, this doesn't happen until you're in court. Again, looking back at these standards, now these are 2 proposed actual standards. So lacking direction from either party, you're going to formulate 1 or more reasonable proposition pairs that address each party's, and notice this word, assumed interest. Not necessarily their definite interest, but it's what we're assuming would be their interest. The next part, laboratory shall reassess the data under a new pair of propositions if presented with a reasonable request, supported by the data, presented in a timely manner from either party regarding an alternate proposition pair. So this is a shall. This is actually directing you that if you follow these standards, you shall actually be open to this and do these kinds of calculations. So Cal DOJ actually has this concept in our reports. So this, put it in colloquial terms, if you think we screwed up in the propositions, tell us. And as long as it's reasonable, the timely discussion, and we can do it with the software that we have, we will do it. Now, could there be abuse? If someone's going to say, here's 500 new propositions, that's not narrowing down to a best representation necessarily of a particular position. So we're going to certainly limit the number of additional requests. Also, big thing, each party can't control the other person's theory. So the prosecutor can't say what the defense theory is. The defense can't dictate the prosecution's theory. So if the prosecution wants to say victim and suspect, the defense can't tell the prosecution, no, your theory has to be only defendant or only suspect. Similarly, the prosecutor can't say, no, you can't consider relatives. So, you have to keep that in mind. Now, with a lot of softwares, the number of contributors may be locked in to have to be equal. In that case, you have to be a little flexible. Comparing to alternate persons of interest, so, in our agency, we would be open to having an alternate person for that denominator proposition, but it has to be a real person. It can't be some virtual person that's actually drawn after the fact from the interpretation phase. Got to be a real person. Eventually, you may not be able to solve anyone, you may not be able to answer every question. Sometimes you're just going to have to say, here's the data, you're going to have to go and redo this yourself. Now, cognitive bias concerns might be there for some people, but just remember, if you do all the legwork initially before you then say, okay, now do you have some alternate theory? That's all in the file. It's in your reports. That doesn't go away. So that all pops in at the end. So with that, I would just like to say thank you again for your time, your attention, and go Dubs.
All right, Stephen, thank you so much. That was an excellent presentation. We are actually right on schedule here. So I would like to hand the screen over to Dr. John Buckleton for our next presentation. Thank you.
Thanks. Thank you, Tamara. I have my presentations on the web if anyone wants to download them, so I've put the address up here, and I have hidden a few slides in order to leave some time at the end of today for questions. We see in the chat bar at the side here some good questions coming up. I'm going to try and leave about 20 minutes, so you'll notice if you download the slides, I'm not going to speak to some of them. Excuse me while I have a small technical meltdown. I'm going to try and cover a number of topics today, and the first one I'm going to start with is the number of contributors. This is a quote from a court case in Australia. What's your opinion about how likely it is that there are more than 4 contributors to this mixed DNA sample? I have absolutely no idea, and nor does the prosecution witness. So we get the allegation that the number of contributors is completely unknown and cannot in any way be rationally assessed. And we have the garbage in, garbage out analogy. This is a situation that we have contributed to. I have contributed to myself. And one of the contributions I've made to this poor situation is this graph from the 31 labs compilation we did. So 31 labs across the United States and the rest of the world contributed their internal validation data, and we processed it in a response to PCAST requests to publish some more data. And we assigned the number of contributors by human assignment. Here you have our assignment on each of these 2,825 mixtures, and across the bottom's known n, and possibly writing known n there was the big problem. I'm going to ask you to look at this part of the graph. This is the 6-person mixtures, and we have assigned them as 3, 4, and 5. So we actually assigned none of them as 6. And you can see we assigned 3% as 3, and 69% as 4, and 28% as 5. And to state the bleedingly obvious, we assigned none of them as 6, which could easily be interpreted as we got absolutely none of them right. And I'm making air quotes around the right, although I realize you can't see that. This is our fault. We presented this graph, and we've been feeding this misunderstanding. The key here is that actually many of these mixtures were made with very tiny minors, so they could easily be things like 100 to 100 to 100 to 1 to 1 to 1. And realistically, those tiny minors are essentially not there. And I wish we'd not labelled the x-axis known n, because it gives the impression that there is such a thing as a known n. If the minors make no contribution to the signal, they're essentially not there. But that's not the main point I want to make about this, whilst confessing to having contributed to the problem. I want to argue that there actually is no problem. And I'm going to start with this graph. So these are 4-person mixtures. And on the y-axis we have the LR using the correct number of contributors. And on the x-axis is the LR for 1 under. And what you can see is that the bulk of the data lie on the x equals y line. And if we go 1 under, what we do is provoke those data that you see in the red box there. We provoke a false exclusion. And the false exclusion is of the littlest one. I just quickly point out, that's the one you don't think's there. So if you've called it a 3 and it is a 4, that's the one that you don't think's there. And indeed, if you hark back to my comment about the 100 to 100 to 100 to 1 mixtures, not only do you not think it's there, but it is actually essentially not there. Those are the true donors, and here is the behavior of the false donors. And we see that the behavior of going 1 under in no case provokes a big LR from a false donor. In general, it tends to move them, their LRs, downwards. So the LR is either the same, or in many cases, we provoke a conservative behavior. I'll just round out this section by going overestimating. So if we go 1 over, again, the true donors are the blue dots, and we see they universally lie on the x equals y line. However, in this case, going 1 over does provoke some of the false donors to move up towards a log likelihood of 0, and that is an undesirable behavior. However, at least none of them ever get really big. So for any LR that is large, it tends to stay the same, and somewhat unfortunately, the false donors move up towards a log likelihood of 0. I've tried to sum this up in my color chart that some of you may have seen, and I continue to make some adjustments to this. I'm going to assume that we can get within 1, so we're going to be either 1 under or 1 over, and I'm going to have true or false donors. So for the true donors, you kick out the smallest one, and that's the one you didn't think was there. For the false donors, some inconclusives drop down to exclusion, and I've marked that as green because that's a good behavior. They are false donors, and we do want them excluded. For 1 over, the big ones stay the same, and the smallest one drops 2 orders of magnitude. I just want to point out that's conservative. I don't feel I can mark it as a good thing because it's false conservatism, but I've marked sort of neutral as blue. For the false donors, some exclusions come up to inconclusive, and I've marked that as red. So that would be interpreted as a bad thing. However, at least none of them in our hands have ever got big. The new bit I've added to this is that we have in StarMix now got a method by which you can set the prior. So if you believe there is a trace contributor, you can constrain it such that the new additional contributor has to be very small. And this improves the behavior a bit. Basically, all the known donors stay the same now. But again, I've marked as red, some exclusions come up to inconclusive. Now, I've been working up this sentence because as long as your LR is big, then you are either using the correct number of contributors or you are otherwise provoking conservative behavior. So I think uncertainty in the number of contributors can be readily managed. I don't believe it is garbage in, garbage out. I think that, first of all, it's never known, and we ask you to make your best assignment. But it's never known, but if you are incorrect, and I need to make air quotes around incorrect, you will either be using the correct number of contributors or you will be provoking conservative behavior. Now that's the state of the work as of about 6 months ago when this absolutely hallmark paper by Slutin and Caleb came out. And this paper was a mind-opener for me. Slutin and Caleb are both gifted mathematicians, and this paper is written to be read by more mathematically oriented and can be a bit of a challenge, and I actually had to have help from Slutin and Caleb to get through it, and I acknowledge and appreciate that. But here is one of their key statements. The LR will be determined as the weighted average of LRN, each with the same n in the numerator and denominator. So, I'll just say that again. The LR is the weighted set of LRs with the same top and bottom. If Slutin and Caleb are correct, and I believe they are, we can stop fretting so much about trying to have different numbers in the top and bottom. Here is their core equation, and I recognize the challenging aspect of this, so I'm going to go through it a little bit slowly. I'm going to cancel this at the end here, but I'll just uncancel it for a minute. This is the probability of a certain number of contributors, let's say 3, under the prosecution proposition, and a certain number, let's say 4, under the alternate proposition. But I want to point out that there is no profile of the perpetrator or the person of interest or the crime scene. So this is what's called the prior on the number of contributors. You are not allowed to look at the profile, and you are not allowed to look at the person of interest genotype. Slutin and Caleb argue, and I think they have some significant credibility in this argument, that if you don't know those, then why would you have any reason to think the number of contributors would be different, top and bottom? So I'm going to cancel those, which leaves me with this thing they call the weight, which is the weights for the weighted average we spoke of earlier. And I think my next slide will just tidy that up a bit. You are now asked to assign n the number of contributors, and you are now allowed to know the POI's genotype. You are allowed to know the crime sample profile, but you assume the POI is not a donor. Therefore, having his genotype is not a lot of help. Now, I would claim this is what we've done all our lives. We look at profiles, we do not look at the POI's genotype, and we attempt to assign a rational number of contributors. And we suggest you don't have a sneaky peek at the genotype of P, and you make this assessment. And again, I just repeat, this is what I believe we've done all our lives, and it suggests that we should give our best assessment of this. Further, it would suggest there is no justification to look at the genotype of the person of interest and the crime sample and add one to fit P, and I've even put the air quotes in this time. I am aware of some behaviours where they say, well, the top line is assuming P, therefore if you need an extra one, put it in. If Slutin and Caleb are correct, and I believe they are, then we should cease that behaviour. It also suggests there is little justification for different n in the numerator and denominator. Now, if I've taken you with me on this journey, and I recognise that I've been very brief and brutal with it, you will see why I find this a mind opener, because this is truly mind opening. We now I guess are justified in doing what I have always felt is the correct behaviour, which is trying to assign the number of contributors without reference to the person of interest at all. StarMix has the capability now of doing this for you in versions 2.6 and higher. Now I'm going to just close off that, and I apologise for saying StarMix often enough. I recognise this is a generic webinar, and I apologise that my knowledge base is now largely built around StarMix, but I do recognise that some other softwares can do these same behaviours that I'm speaking of. I want to talk about verbal scales now, where I can be truly generic. And the background for verbal scales are that Dr. Ian Evatt and myself started trialling these in the 1980s, and we were very excited about the prospect of doing something with these to help understanding of evidence. And our excitement has been completely falsely founded. They have produced nothing but trouble. At one point, the United States had a plethora of verbal scales, and the diversity between us emphasized both the subjectivity and arbitrariness of these verbal scales. And at least partly at my request, but probably also by requests across the United States, SWGDAM got together and have put out some recommendations. And I'm going to speak directly to those. I want to start by talking about adventitious matches. And I specifically want to emphasize this because somehow we have given the impression to our judicial colleagues that adventitious matches should not happen. They can happen, and they always could. Things such as the random match probability was an attempt to estimate how often an adventitious match would happen. And this is not new, but somehow we've created a very false impression. I want to acknowledge the 60 collaborators we have on this internal validation paper. This is a compilation of data across America and more broadly across the world. And it's a document I'm very proud of. And it was constructed in response to PCAST. It is the largest study of this size undertaken. Here are some of the data. There are 28 million false donor tests here. So those are comparisons to known non-contributors. And here is the top part of a list of 20 highest false contributors. I'm just going to put, I think, a little square around that number there. The highest LR from a false contributor was 500,000. These data were presented by Dr. Tamara Moretti at a conference in Texas, and deep consternation was expressed by the audience. In fact, I think a little microphone will appear here. A member of the audience stood up and said that this was a microphone drop moment. Now, I understand that a microphone drop moment is a young person's expression for an outstanding event that is truly staggering. And deep shock was expressed at the presence of adventitious matches of this magnitude. And I guess by corollary, if adventitious matches of this magnitude can happen, well, what on earth should we do? In fact, that 500,000 is not the biggest one that we've detected. In this paper here, we have one of 730,000. Now, these should not be this surprising, because if you simulate sufficient profiles, you will eventually simulate one with the right allelic composition to match the mixture and produce a high LR, and that is the correct result. But I want to dig into this a little bit further, because not only is it expected, but it turns out that the trials are actually coming in at below the expected level. And I want to work through that with you a little. So this introduces the concept of false donor testing. I hear you say, what on earth has this to do with verbal scales? I'm hoping that this will all tie up beautifully in a minute. False donor testing tests false donors against the profile. People either use a database of staff, but obviously a database of staff is unlikely to have more than 1,000 people, or you simulate, and we tend to simulate because we need vast numbers of false donors. You run them against the profile with your system, and you record the results. And I've got and present. I don't know whether we would present these in court or not. The problem is that to test an LR of X, you need at least X false donors, and some of our LRs are of the order of 10 to the 20, and that would require at least 10 to the 20 false donors, which, just to state the obvious, don't exist. Turing informs us that an LR of X should happen less than 1 in X of the time. So an LR of 1,000,000 should happen less than 1 in 1,000,000 of the time. And I present to you the reference that reprises that. That's the work of Alan Turing, Alan Turing was a mathematician involved in breaking the Enigma code during the Second World War, and him and his colleagues are often credited with saving many millions of lives by shortening the Second World War by about a year. He was also a long-distance runner, so here he is running a long distance, and here is a picture of the Enigma machine used by the Germans during the Second World War. His actual statement is the expected factor for a wrong hypothesis in virtue of any experiment is 1, which is lovely language, but quickly translated, the average LR for an HA true test should be 1. Which brings us to the verbal scale put out by Swigdam, and often claimed to be arbitrary, subjective, and without any form of support. Now, this is rather unfair criticism, and I'm just going to show you a bit of a response here. So, would you please look down this list here, and we see that the first category is LRs from 1 to 2, and that is to be described as uninformative. And Turing tells us that an LR of 2 should happen less than half the time, which is, that's not going to be too impressive. Let's do perhaps one that's a little more exciting. The category 2 to 99 will be described as limited support, and that should happen less than 1 in 99 of the time. Now, here are the rates of occurrence of these in these 28 million false donor tests. Just remind you, the largest experiment of this type undertaken and involving a broad range of laboratories across the world. So we see that the actual rate of false donors is coming in at 1 in 312, which is markedly less than 1 in 2. So that complies with Turing's rule, and in fact we see the rate of adventitious matches of this fairly limited nature is less than expected. But let's look at some of the others. So 1 in 318 is less than 1 in 99. 1 in 18,000 is less than that number, and 1 in 1.4 million is less than 1 in a million. We see that in all instances that we have examined, the verbal scale prediction is predicting, or the number of adventitious matches are coming in at less than the expected rate. Now this represents some form of empirical calibration of the verbal scale. Indeed, the word limited would have different meanings to different people. However, we can now give it numerical statement, so limited support should happen something less than 1 in 99 of the time, and in fact empirically it's 1 in 318. Now if you go to my actual slides, you'll see I have quite a lot more material on this there that I hope you might be able to look at yourself sometime. More recently, this paper here came out. I'm hoping some of you can see this up the top here. Forensic Science International Synergy, and it's 2019, it's quite recent. Juror Comprehension of Forensic Testimony, a Literature Review and Gap Analysis. And I see it's from RTI International, so somewhere pretty close to where this webinar is coming out from. And this is a really good paper. It's doing a holistic assessment of methods of presenting evidence. And I think I'd read it as coming out pretty strongly on the side of the verbal scale, and we could take that as some support for the use of these scales. Now I want to move on to the subject of calibration. I believe this to be the next most exciting phase of validation of probabilistic genotyping. And I reprise back to David Balding's earlier statement that there is no correct LR. David Balding said that, and Steele and Balding have published that, and this concept has been picked up with great excitement by members of the independent forensic community, and essentially they would argue that if there is no correct LR, how on earth could you ever validate a software because you have no correct answer to compare it against? And the analogy would be that if you were validating a pair of scales in your laboratory, you'd go out and get some standard weights and put them on the scales and see that you got an answer somewhat near the weights that you had. And then they'd say, well, you can't go out and get some equivalent of standard LRs, an LR of 1,000,000, and put it onto your probabilistic genotyping software and see that you get 1,000,000. Therefore, your testing is somewhat immaterial in that, yes, you get an answer, but we have no method of scoring it as correct in any meaningful sense. Now, I'm not sure that that's true. It's true in part, but it's not true in the broader range. And those two people I referenced back here, I'll just put them back up, Ramos and Gonzalez Rodrigo, I think have made a hallmark breakthrough. And I'm going to talk about rain, and I went on the web and tried to get a weather presenter, and I got this slightly cheesy looking guy. So here he is, and as you know, he says things like there's a 50% chance of rain, and it looks like there's a 50% chance of rain in Idaho from where his hand's going. So how could we check him? Well, what we could do is collect all the times he said 50% and see if 50% of those had rain. And this would at least show that he is in some way rational about his predictions of rain. Can we do that for DNA? Well, we have our 28 million false donors, and it turns out there are 10,297 true donors. So if we put those all in a great big pile and mix them up and picked one, the prior odds that it's a true donor would be that number I've put down there. As you know, the posterior odds equals the likelihood ratio times the prior odds. So each likelihood ratio could be turned into a posterior odds. And once you have the posterior odds, you can convert those to a posterior probability. So we can end up with the posterior probability, which is the prediction of how often that person is the true donor, and it's the equivalent to his 50% rain. Then we check. We empirically go out and observe how often we are correct. And here is a graphic of this. And I recognize that this is not immediately readable. So would you please see range of posterior probabilities? So here is a range from 0.977 to 1. So the posterior probability prediction came out of that. We had 4 false donors in that category. And we had that number of true donors in that category. Therefore, the fraction of donors in that category who are true donors is 0.9995, and I'll just write that in there. And we see that this is the expected result, somewhere between that, and we see that indeed the observed result falls in that category. So here's the next number. So there are 342 true donors and 5 false. But when we do the maths, that comes out as 9856. And we see that's not in the category, it's above it, which means that true donors are happening more often in this category than expected. Or reversing that, false donors are happening less often than expected. And this is part of the evidence for my earlier statement that the number of adventitious matches is actually occurring at less than the expected rate. And you can see that I have bolded this, and I'm going to bold all the ones that are above the category and are therefore conservative, and the ones that are not above the category will not be bolded. And what we see is that we are right too often. There are not enough false donors up the high end here. There they are, there's all of them with the bolds and not bolds, and we see that up the top end, they're all bold, and this one of course could never be above the category because you can't get above 1, so this one never stood a chance of going bold, but please note, he's nudging right up against that top edge, and then all the high categories we have too few false donors, so false donors are occurring at less than the predicted rate. And of course it has to add up. So this huge category down here is the one that pays back all the extras. And this is where the false donors are living at this very low posterior probability, which is where we want them to live. So I'll just click back up to the paper here. I reckon these guys have made a breakthrough. I think this is a way we can truly calibrate the LR. This is as close as we're going to get to having the little weights that we put on the scale. We take a big sample of likelihood ratios from true and false donors, apply this calibration, make a little table like I showed you there, and we are able to show that the prediction from these systems is actually conservative in most cases, that false donors are occurring at less than the expected rate. Again, you'll find I've got a whole lot of hidden material in the web page there where I've put the presentation. And I've dropped that just so that we fit in for some of these very good questions I can see. Because I want to end with the subject of communication. I believe this to be the key issue we need to work with in probabilistic genotyping. And I believe that the key issue is not such things as Markov chain Monte Carlo. I believe that just isn't creating a problem, that it's actually the weight of evidence that is producing the difficulty. And I will just quickly introduce Professor Alan Jamieson. So Professor Jamieson is a prominent defence advocate, and he's director of the Institute of Forensic Science, the Forensic Institute. It's in Scotland, and it has 1.5 staff. And he says no one understands the LR, and by extrapolation, well, maybe not even by extrapolation, he may have explicitly said no one understands the LR, therefore you shouldn't give it in court. It's too risky to be understood, and since you can't present an LR, you shouldn't do probabilistic genotyping. And if Professor Jamieson is correct, then that would suggest we need to put aside the single most powerful tool that's been developed for DNA interpretation. So the issue comes about from placing a likelihood ratio in some sort of context. And I noticed that many of the questions, and I'll just acknowledge Richard Torrey's put some very good ones out there, talks about what we should do with the prior odds. And I heard David Balding also suggesting, I hope he wasn't suggesting we give the prior odds in court, but he spoke a lot about the prior odds. We are ubiquitously advised not to touch them, that they represent considerations of evidence that are not our business and we may not even have heard, and that they are for the fact finders to assess them. The difficulty is that it is very unlikely the jury will have any numerical thoughts of a prior odds at all, or even recognize the word prior odds. So what should we do if asked to do something about expressing the context of a likelihood ratio? Well, what is happening is that people want a posterior probability. They want the probability that Mr. Smith left the stain. And I have been trialling in my head and in court statements of this ilk, and I'm going to put it out there for your thinking. A statement about the probability that Mr. Smith left the stain can only be made from all the evidence, not from the DNA evidence alone. The DNA evidence by itself increases the odds that Mr. Smith is the donor LR times over what they would be from all the other evidence. This represents extremely strong support that he is the donor. And of course I'm suggesting we end this sentence with the Swigdam verbal equivalent. Now another possibility is that we could say evidence of this strength would occur less than 1 in LR of the time from a random donor. This has come under some considerable criticism in that it's like giving a p-value, and can I just acknowledge this paper here again by Martin Kriver, Ronald Meester and Klaas Slooten, and you might recognize Slooten from Slooten and Caleb. P-values should not be used for evaluating the strength of the evidence, and they emphasize that the LR is the best summary of the evidence. What are the concerns over flipping it upside down? Flipping an LR upside down, so an LR of 100 we turn upside down and say this would happen less than 1 in 100 of the time. Well, there's concerns about the pseudo-frequentist expression. There are other profiles nearby, so not at 100 but say at 90, and if you go to the slides I've hidden you would see that I would have introduced that. And we lose the posterior equals the LR times the prior construct. We are also accused of trying not to change from our frequentist past. Now, I want to acknowledge all of these criticisms, but possibly I'd like to suggest, my thinking's still evolving, but no meaningful harm happens if we do this. But I want to go now to the theory of communication. So the theory of communication suggests that we have an encoder, who is the person who is attempting to send the message, and a decoder, who is the person trying to receive the message, and that there should be feedback between these. So the sender says something like, "I think the dog is black," and the decoder says, "I've heard you say you think the dog is black." So the encoder then goes, "Right, I know I've conveyed the impression that I think the dog is black." We acknowledge that there is noise, and noise is not to be considered as necessarily a sound, such as a jackhammer outside, but as all the various disruptive influences that could disrupt this communication. And we need to think about this now in the context of the question and answer format of most court proceedings, at least in the adversarial environment. That we seldom have any meaningful form of feedback with the jury. We may be able to read their body language to some tiny extent, and I certainly acknowledge I've seen members of the jury sound asleep while I testify. And on even more rare occasions, we may get a question from the jury, and that is valuable, but it's not universal. And there may also be deliberate noise. One or other or both of the legal participants may try to disrupt the communication mechanism by many of legal and justifiable mechanisms. I want to give a plug for this book, Robertson, Vigno and Berger. I think it's the best introduction to likelihood ratios of which I'm aware. Bernard Robertson is a lawyer, and Tony Vigno is an operations scientist, and Charles Berger is a gifted mathematician from the Netherlands. And I want to point out the lead author is a lawyer, and I believe this is written in a very accessible way, especially chapter 1, a very accessible way for the introduction to likelihood ratios, and I want to commend it. They have some absolutely great analogies, but in my view they are too long, and I suspect you could not do them in court. I think you would be stopped by one or other of the participants or His Honour. And I want to point out that there is no way we can solve this from one end. So what I have here is the speaker, and I've put it in capitals, and it looks like he's yelling, but I don't mean yelling. I mean something like really trying to concentrate on the message we send is just one tiny part of this entire construct. And I do not believe we are going to solve this problem from one end. So up the top there you'll see I say saying it better does not guarantee understanding it better. And we have this situation with no feedback and deliberate noise, and many of us are concentrating on trying to say the LR in a better way. I don't think it's going to be enough. I'd like to come to my conclusions. The number of contributors. The LR is actually stable over the number of contributors, and I reject the garbage in, garbage out analogy. Adventitious matches do happen. That's meant to say matches, not matched. Adventitious matches do happen, and they're actually happening at less than the expected rate. I believe we need to de-fear the community over this. I believe that we should put our eye on the work of Ramos and Rodrigo Gonzalez. I believe that is a breakthrough. It's called calibration, and I believe it is going to be a highly valuable tool for validation of ProbGen systems. And I believe communication cannot be fixed at one end. It is going to require the help of the legal community. I'd like to make some acknowledgements, if you'll just bear with me, please. I have NIJ funding that helps underpin much of this work, and the opinions or assertions are mine, as are indeed the errors, not the US Department of Justice. I've been having very valuable discussions with Professor Bruce Bedoli, who has contributed to my thinking on this subject. And Lynn Garcia organised a meeting of the Texas Forensic Science Commission. They had a meeting on basically the presentation of probabilistic genotyping in Texas. And I think it was a highly valuable meeting. It's recorded on the web, and it's very lengthy, but I think worth a listen. I want to recognise not Josh Vickers and NIJ for doing this, and Tamara Moretti has been very influential both in organising this and in the content presented, and I wish to acknowledge and thank all these people. That's the end of my talk. I hope I've left some time for questions. I see we've got 14 minutes left. I had hoped to leave more, but I'll turn the presentation back over to whoever leads this.
Thank you so much, John. While you have your slides up, there was one question about the website where your slides can be viewed. Do you have that on any of your slides back at the beginning?
Putting it back up there?
Yes, please. Okay, thank you. So yes, thank you so much, John, and I appreciate you bringing up these topics as the things that you're discussing seem to be what we are discussing as a community: adventitious matches, this question of are results inconclusive, how do we communicate it, and in particular, given since our reports in most instances need to stand alone as something that can be understood by law enforcement or the legal side of the house, and so oftentimes we don't get to have those oral communications. So thanks for bringing all of these topics to our attention. We will continue our discussions on those very topics in some of our future webinars. So I'm going to attempt to pull up my screen where I have tried to summarize the questions or list them here into topic areas, and I would invite any of our speakers here today to jump in to speak on any of the topics here. I don't think we have time to get to all of them, but this was an interesting one here, just a general question about, is it possible to say what effect a relative of a victim would have on an LR? Does anyone want to jump in and speak to that?
My understanding of this question, I think it's from Richard Torres, is that the numerator would be victim's child and POI versus victim's child and unknown. The answer is yes, that is possible. If we consider two scenarios, the victim's child is genotyped, then it's absolutely straightforward. If the victim's child is not genotyped, then the current software that I'm aware of cannot do that, but it is doable. It could be done by hand, be enormously tedious, but it is at least theoretically achievable.
I'm thinking too, John, of the scenario where you have a situation in a home where you have a child and a mother who happen to be mixed, and then say a question of incest, and then we have a father. So we're looking for the father as the POI, but we have a mother and a child sharing DNA in that mixture. Did I confuse the issue?
You've brought me to my knees, Tamara. I'll just defer at this point. I think.
I think what I'm envisioning is we have a 3-person mixture that looks like a 2-person mixture, and unless that third individual is in trace levels, we might not even detect their presence. I don't know if that was any aspect of what the question was getting at. All right, let's move on. The first two questions under proposition setting, I think Stephen certainly will make, he has said, his proposition flow chart available, and all of our presentations, barring any other restrictions we encounter, we will try to make those all available on the FCCOE website here with the series. And we will have a whole lecture on number of contributors, so maybe we'll unfortunately table that one in the interest of time here too. But here's a question about proposition setting. Can the defense proposition simply be that the prosecution proposition is not true?
Tamara, I'm a little bit shy to be the only one answering, so please, if anyone else wants to kick in, do so. But I would argue that that should be the defense proposition in all cases. The prosecution proposition is not true. So the defense should be entitled to the sum of all propositions that are consistent with exoneration. And there are some sensible ways to simplify that in such a way that that safeguards the legitimate interests of the defense. So I do try to teach sensible ways to do that, and I wonder if maybe there's room for us to put together another paper on this that would show how such approximations can be done.
Okay. Stephen, I don't know if you're there, if your mic is muted, or Mike as well. On the next question, why would the arguments of the prosecution or current claims for the defense come into propositions? If the defense wants to claim an unrelated individual, you may not even know that until the time of trial. Wouldn't you just determine all of the possibilities and proceed, as discussing now about relatives? Stephen, are you on the line and able to speak?
Sure, yeah.
Okay,
so the reason we talk about, the claims from the prosecution and or defense are that, we're asking, the jury is trying to make up their mind. And if the only information we've been able to give them about the probability of seeing the evidence as in an alternate proposition is for a proposition that is completely unrelated to what is actually being argued, then they don't really have as much information as ideally they should or could. And you're correct. Unfortunately, a lot of times you don't have the answer until you're in trial, if you even have it then. I can't speak to all softwares. I know that, in our StarMix reports, in instances where for the likelihood ratio there is only, one person who changes from, there to not there in a particular likelihood ratio hypothesis pairing, proposition pairing, you would actually get in the report the relatives calculations also. You'd get, if that alternate person was unrelated, if they were full sibling, parent-child, etc. So, while we don't issue all of the options in our reports, we do have, a bunch of things effectively in our hip pocket and discoverable. Again, in StarMix, in those instances, there is also a calculation called the unified calculation that would incorporate prior probabilities of given a particular population size and a particular, number of kids per generation. Here there's a prior probability a randomly selected person would be unrelated, would be a relative of a particular level. And it kind of brings all of those LR calculation denominator probabilities together into one number. So, it's great to have all those things, but, again, there is just a practical reality that sometimes, you're not going to be able to address things on the fly. That doesn't mean that it's not the, optimal situation to say, yes, you should be able to declare your proposition, and in the best world, we'd be able to give you that number so that the jury could actually assess the probability of that evidence under that proposition. So sometimes we run into practical versus, idealistic issues. But this is also part of why we did put that wording in our report, to try and encourage people, especially if they have a real firm theory. Even, again, they're not required to have a theory. I'm not trying to push the responsibility onto the defense that they have to declare a theory, but if they have one, we'd be glad to actually try and be able to present probabilities that are relevant to that information.
Very good. Stephen, are you able to read the next question, and did you want to comment on that?
So again, I don't think we're making the decisions for the jury, kind of jumping to that last bit. We are still seeking for the evidence, in the sense that, if someone tells us how they think the evidence got there, we are still using our science to work out the probability that you would get those results under that theory. So I guess I'm getting hung up on the phrase to make decisions for the jury. We're not making decisions for them. We're trying to inform them.
Let's see. Yes. Okay. So we're about ready to close, and so I just wanted to let everyone know that the questions that we weren't able to get to in this session, as well as the last session, I am keeping track of all of the questions, and so our intent is to follow up with a concluding session after at the end of the series, to make sure that we are addressing everyone's questions to the best of our abilities. So I wanted to thank our speakers today so much for sharing their experience and information with us. I think we are well on this journey, and I also am grateful to Gerald Laporte at NIJ and his staff for supporting this effort, as well as the talents of Josh Vickers and his staff at RTI International for helping us in this process. So in two weeks, I hope you all have the chance to work through those examples that Mike Coble went through in his lecture. He'll be coming back to those, kicking off our next session, in which we are also going to be having a chance to see and learn about 3 of the different software systems. We decided to focus on 3 of the fully continuous systems. We're going to be hearing from Mark Perlin about TrueAllele, John Buckleson again on StarMix, and Peter Gill on Euroformix. So we will be able to start fitting these concepts of the likelihood ratio into the process via the software that is generating those numbers. And Mike is going to be doing a comparison of sharing some information about comparisons of the different systems and their capabilities. So I will hand it over to Josh for final concluding remarks, but thank you all so much for joining us today.
Right. Thank you so much, Tamara, and thank you, obviously, to all of our presenters today. We are going to go ahead and close things out for the day, but in doing so, we would like to make everyone aware that this is the second module in our workshop series. We will have quite a few more. The next one will be in 2 weeks from now on May 22nd. So be sure that you register for that. The registration went out this week. So be sure to check our website, as well as check the newsletter if you are subscribed to that. If you are not, please do so at our website so you can stay current on all of our forensic offerings. Obviously, we would like to thank all of our presenters today, Dr. Balding, Dr. Coble, Stephen Myers, and Dr. John Buckleton, for their countless hours of research and taking the time out of their obviously busy days to present here today. We would also like to thank all of our participants for joining us. We had another great turnout over 450 attended today's event. So again, just fantastic from the forensic community to come out and learn from these amazing speakers. If you could take a few moments before you leave today to complete our survey, it is back on the original registration page, or you can find it directly below the closed captioning on the right-hand side. There's a small button that will continue you on to the survey. It only takes a few moments to complete, and your feedback regarding our workshops, webinars, and events is valuable to us. We want to make sure that we are providing you with the best content and the best experience possible, the forensic community. So please make sure to take a few moments and do that. Also in the chat, Tyler is going to be putting up our social media outlets such as Facebook, Twitter, and LinkedIn. If you're not following us on that, please make sure to do so you can stay up to date on all of our current offerings. Also, you will see our podcast is there, so be sure to subscribe to that, and our website where you can find all of our podcasts, all of our webinars, workshops, reports that we are putting out constantly, new material to you, the forensic community. So make sure you check our website there. Again, thank you everyone for attending today. We greatly appreciate your support, and we look forward to seeing you in the next event.
Recording has stopped.